over the bare bones tutorial on the OS Dev Wiki, which is going to be very interesting for those of you who have never seen the OS Dev Wiki before, because it's very interesting in the fact that it's basically written in first person. There's a lot of eyes everywhere, and the entire community is basically insanely elitist because they all consider themselves professionals since they're operating system developers. We are not going to go over any OS theory today at all. We're primarily exclusively
Over here
over.
is Eugene.
Did someone get the server mute? Okay, I didn't even have to do it. Someone did it for
I got
me. Okay, so yeah, this is primarily what we're going to be going over today. Is basically just how to get a simple Hello World operating system that prints out Hello World for you on the console. And I can demonstrate that right now because I have actually developed that in. Do I have VirtualBox? Let's pull up VirtualBox. If I actually start this up, this is what we're going to be developing today. I know this doesn't look very exciting, but I print out here, hello IEEE, this project was a mistake. And yes, we are basically writing Hello World in the most hard and impossible way, but the benefit is the fact that we are developing our own operating system. So this is a very exciting project because operating system development, of course, is widely considered one of the hardest things you can possibly do as a computer programmer, and it's just such a massive undertaking. But just getting this basic stuff down, isn't that much of a challenge, right? Compared to actually writing the full operating system. Because to write the full operating system, you need to know a bit of OS theory, you need to write your own memory manager, you're really making all the big decisions, right? Especially if you want security features and everything, it can become a real pain really fast. So again, we're not going to focus on actually developing applications or anything. We're not even going to be able to get keyboard input. Keyboard input is a level beyond what we are going to touch today. But what we are going to touch is just the basics, the wrapper, and how you can use C and assembly to basically write your own little operating system. So this is hopefully going to be a very enlightening workshop for everyone, especially if you've been to the past two workshops. We're really going to start to see the assembly and the C come together today in actually developing the operating system. So before we actually begin talking about even developing the operating system, first we really have to talk about what's going to happen when we boot up the computer. So when you turn your computer on, the first thing that's going to happen, at least on older computers, modern day computers use something called UEFI instead of BIOS, but for the sake of simplicity, we're going to assume that we use BIOS, and the most virtual machines are going to be BIOS as well, so this shouldn't be too much of an issue for us. We're not going to have to worry at all about UEFI. So the first thing that happens, when you press that power button, the motherboard is actually what takes control first, not the processor. This is kind of counterintuitive because, the processor is what's supposed to be doing all the heavy lifting. And of course, it is, but that's not the first thing that happens. That on button is actually connected to the motherboard, and the motherboard takes over the second you press the power button. And that calls a chip called the BIOS. And what the BIOS does is it loads in from your bootable hard drive. And you might not realize this when you turn your computer on. Normally you get a screen that's related to your motherboard. For example, I have an MSI motherboard, so when I boot on my computer, I get a big MSI Dragon on the screen. And during that time period, that's when the BIOS has control of the computer. And normally you can press a key on your keyboard to have the BIOS take over control and print things out on the screen. And what's interesting about that is the processor isn't actually doing any of the work for that. That's the BIOS having complete control over memory and everything. So during that time period, you're also able to normally press a key and get access to a BIOS menu. And the BIOS menu is normally where you can configure things like system settings and everything that your motherboard is managing. And normally you're not giving your processor access to any of that, right? So this is before the processor has even basically, been started up. So that is essentially the BIOS level, right? But the thing that happens once the BIOS is done, the BIOS needs to hand control over to the processor. And the processor, of course, the first thing it wants to do is we're not just loading programs in raw assembly onto the processor. We need the operating system so we can actually, run all of our basic features. So the first thing that you would think, oh yeah, so the BIOS hands control over to the operating system. This is not the case. In between booting the operating system and the BIOS having control of the computer, we need to do something called the bootloader. Essentially, the bootloader, what the bootloader does is it moves the operating system code, and it can be quite a bit of code, from your hard drive into memory, into RAM, so that the processor can fetch those instructions and execute them, right? But here's the thing. The second the BIOS hands control over to the processor, what it's done is it's moved the master boot record in the first segment. When we make a disk bootable, you might know about this if you've ever tried to install an operating system on a Raspberry Pi, or even if you've built your own computer. You've probably had the experience of creating a bootable disk. And what that's doing is writing to a section of the disk. Normally it's the first section, which is like the master boot record. And in the master boot record, that is like, I believe is it 512 bytes? I don't actually know the actual number. But basically you have 512 bytes to load more stuff into memory. It treats the 512 bytes at like the first segment of the disk as your code, assembly instructions to load in the rest of the operating systems. Now, obviously, 512 bytes is not enough to load in the entire operating system. So we don't use 512 bytes. Instead, what we do is we have the master boot record load another bootloader, which is bigger, and then that bootloader loads the operating system. So we actually have two stages of bootloader. We have bootloader stage 1, which is the master boot record loading the bootloader, and then the bootloader loading the operating system. Now, if you were really crazy and you really wanted to go, if you wanted to, as they say, roll with your own bootloader, you could write the bootloader from scratch. You could say, okay, the second the BIOS gives control to the processor, I'm going to have my code in the master boot record loading my own operating system. This is not a good idea. Well, at least for us, because we do not have 500 hours to write our own complicated, fancy bootloader that does all of the fun stuff that we want it to do. And there are very nice standards that have been written, like the multi-boot standard, which basically allows us to have access to a standardized way of loading multiple operating systems on a computer. So it's kind of modularized. We've kind of modularized the bootloader out of the equation, and we're going to be using grub as our bootloader, which is a good multi-boot bootloader. So we could have multiple operating systems as well, and have the bootloader take care of that and find them independently and load them. So the next thing that happens is once the bootloader is done, it's going to hand control over to our operating system. And the bootloader needs to know an entry point into the kernel. And it will basically call and jump to the start location of our kernel. And the start location of our kernel is going to, of course, be written in assembly language, because we need to do a few things before we can set up our C kernel. Because when you call a C function, it expects a stack to be set up, but as you'll see in the next section, we don't actually have a stack set up coming out of a grub booting. So finally, we're not going to be doing Linux. This is basically going to be the endpoint, right? We're not going to have an init process. We're not going to have a user prompt. The kernel would normally be setting all of this up for us if this was a real operating system, but it's not. So normally, of course, Linux, it's setting up init, and then it's setting up the user prompt with all the user commands. We're not doing any of that because we are not writing a real operating system. We're just having the kernel print out hello world and then die. That's all we're doing. So the first thing we need to talk about when developing an operating system is building a cross compiler. So you're probably wondering, what is a cross compiler, first of all, and why do I need it? And I'm glad you asked, because that is actually probably one of the most common questions that we get. So if I actually go back to the bare bones tutorial, which we're going to be working off of, you're going to see that the first thing, the main article, the first thing you need to do is build a cross compiler. And of course, right next to that, they say, well, they have an article called "Why Do I Need a Cross Compiler?" Because this is, of course, the first question you should be asking. So what a cross compiler is a compiler on your system that targets a different machine. So say I wanted to build Windows EXEs on a Linux machine. I would write a compiler that targets Windows and compiles exes even if I couldn't run them on my Linux machine. And that's a cross compiler. And the reason we need to do that when compiling for our operating system is because we do not want to target an existing operating system, and all existing distros of GCC and other C compilers and assemblers target Linux or Windows by default. So for example, I'm going to take this gcc dump machine command, and I'm going to open up my Windows command prompt here, and I'm going to say gcc dump machine. Give me that. Copy, paste. And let's see what we have. So we see that my GCC distribution is targeting MinGW32, which is essentially the Windows version of GCC. So it's a 64-bit machine. That's x86-64. That's our processor. W64, Windows 64-bit. And we're using MinGW32, which is like the special wrapper that we have, so we can use GCC on here. So that means that every time we compile things, it's basically going to know that we're on a Windows machine, and it's going to optimize things as if we're on a Windows machine, and it's going to have a bunch of different special directives put in and everything, and we do not want that. So if I compile by default, this is going to give me a Windows exe. And the same way, if we were on a Linux distro, if I go into WSL right now, and I've run the same thing, gcc dump machine, now we see we're on x86-64 Linux with GNU. Essentially, we don't want either of these. We don't want to target our executables to Linux or Windows. We want to target a raw processor. We want basically to target just raw x86. And I should have mentioned this at the beginning, we are not developing a 64-bit operating system. 64-bit operating system is slightly more complicated than a 32-bit operating system. You have to switch into long mode, which I'll go over later. So we're just going to be working in 32-bit, right? So we want to target a generic 32-bit processor architecture without an operating system. And that's essentially why we are building a cross-compiler, because we are working down at like the hardware level. We don't care about the operating system. We don't want any of these operating system constants defined. We don't want to be able to use, especially when we're talking about libraries and everything, we don't have access to any libraries whatsoever. Every single library we have to write basically ourselves from scratch. The ones that use operating system features like malloc and everything, we do not have access to that because it is not freestanding. It depends on the operating system for its features. And since we're writing the operating system, if we want malloc, we have to write those features ourselves. And despite the fact that there are some freestanding libraries like string, string is not actually a freestanding library. You actually have to write all of the string functions yourself. So if we just briefly go look at my operating system code here, we'll actually see that I've written my own string library here with just a few string functions like string length, string copy, and string compare. You really have to do everything yourself, and that's kind of what's fun about writing an operating system, right? Is the fact that you do get to implement all of this yourself, and you really get to learn along the way. Oh, so that's how this is probably implemented on my own system. Okay, so I hope everyone understands the need for a cross-compiler and the previous slide, which was the everything about the boot sequence. Do we have any questions before we move on to actually building our own cross-compiler? Because that's going to be the first thing we go over. Hopefully, I hope for those of you who are following along, we are going to be building our own cross-compiler tonight. So let's, any questions, first of all, about booting, any of this stuff, or what a cross-compiler is, or why we need a cross-compiler? I am happy to explain further if anyone needs any further clarification. All right, I'm going to assume that you all understand the purpose of a cross-compiler now. So we are going to move on, and we are actually going to build it, and we are going to build it from this tutorial, which is going to be very, very painful because I am envisioning lots of suffering. Can I get a quick, so in case you didn't see, I said before the presentation to install a virtual machine for Ubuntu. So you can either get VirtualBox and get a virtual machine running right now, or you can follow along anyway and just not build the operating system. There are instructions on this page, I'm linking the page right now, to compile and get all of these packages on Mac. However, I cannot help if you get any errors because I will not be able to interpret them. As you can see right here, these are the dependencies that we're going to need to build our own GCC. We're basically using our system's own GCC to compile our new GCC cross-compiler targeted at a generic architecture. And we're going to need all of these packages right here and a few more secret ones in a list that I've found are useful. And we are going to basically build our new compiler from scratch, from source, essentially. And it's actually going to take a bit of time. So while everyone's stuff is compiling, we are going to, I'm going to talk while that happens. Anyway, so I'm curious how many people are actually planning on following along and coding themselves. So if I could, I'm going to type in Discord right now. React to this message if you are if you are actually doing the coding. And if you are doing the coding, react with something. Yeah, just click on that hand emoji, which someone just deleted. Yes. Click on that hand emoji. I just want to make sure we actually do have a few people following along, because otherwise there's no point to me. It takes a really long time to actually build this stuff. So if we can avoid the building stuff and just do show off, then we could have done that. But since we actually have people who want to build it tonight, we will go over the entire build sequence then and actually try getting everything set up. So my new question is, do I want to do this from scratch? And I think the answer is going to be yes. So I've done this once before. I already have a cross compiler. So my cross compiler on my Linux machine is actually in my home directory. Oh my God, I didn't expect there to be, oh, this isn't my home directory. This is my Windows home directory. I want my Linux home directory. cd os ls cd s cross ls cd bin, and these are this is what I've been using to build my own stuff. Yeah, Kino, I recommend getting a virtual machine and doing it on Ubuntu, because I do not have faith that Mac is going to be well suited for the task. While I'm sure it's definitely possible. You know, I thought that they listed. Okay, so before we go to all the problems of building from source, down here you actually can see there's pre-built tool chains, which means people have already built all of these for various systems, but they are not guaranteed to work. So I'm reluctant. I'm very reluctant to recommend downloading these as the EXEs and try using them rather than building it directly for your own system. But if for some reason you feel like you want to try these and not go through the pain of building, in that case, yes, you can you can attempt to download one of these targets. But we're also going to need GCC. I don't know if this comes with the GCC and everything. So let's actually just go through the tutorial that they have. So to prepare for the build, first thing we're going to need to do is install all of these packages. So I'm actually going to create a new directory for this. So I'm going to cd back ls cd back ls. Where are we now? Okay, I'm in my home. So I'm going to call this, I'm going to make this a new directory. So let's start off by making a directory. mkdir, and I'm going to call it, let's call it, you know what, I'll call it osWorkshop. And I'm going to just be building everything here. So the first thing we need to do is actually get all of these dependencies. So I hope you can see this here, that we have, we need basically this entire list of things. And the reason we need this is because this is what GCC requires from us to be built. So let's actually go about installing. So I'm going to be doing a Ubuntu installation for this. So basically we have to install this entire list of packages. So of course, to go about that, you do sudo apt install. There was an interesting discussion earlier about apt-get versus apt. Did we ever come to a conclusion about what it was? What the difference is? So the first thing we want to do is install build essential. Now you might notice that you already have some of these. That is the operating system. I'm going to power that off. Goodbye. And goodbye VirtualBox window. And here's my terminal. So essentially, we're installing all of these packages. Uh-oh. Do I not know my sudo password? There we go. So I already have all of these packages on my machine, but you're going to want to install literally all of these. So this is probably going to take like a good 10 minutes to install all of these, if not longer. So while we wait, Dan, would you like to explain to us what the difference between apt and apt-get is? Because I don't know, and I'm honestly pretty curious because I've used both before.
Okay, so apt basically combines a few of the commands or functions from the apt-get library and the apt-cache library. It's a newer command, so that's pretty much the main difference between the two.
Oh, that's very interesting. From now on, I will use the newer version.
It's in the general chat, by the way, for anyone wondering.
Oh yeah, let's take a look at that while we wait. While everyone who's following along, everyone who's doing their installations. Once you were done with your installation of all of these packages, give me like an @ or something. And the build process is also going to take like 20 minutes, so we're going to be sitting here for a while. So I'll probably go over the code while we wait. But anyway, let me lay down the. Hang on. I will lay out the groundwork for letting us know you are done. React to this message if your packages are installed. Really? Someone installed all of those already?
I installed it earlier.
Oh, yeah. I did lay down in general what packages need to be installed. If you, I'll actually put down the list as well, which is right here. We're actually going to need a few more. We're going to need grub common, grub PC bin, osWorkshop, and we actually don't need Doxygen. I was trying to use Doxygen as my C documentation generator, and it does not work very well for C. It works much better for things that actually use classes, which is unfortunate. Thank you, Dan. That's perfect. The list of packages. All right. So I'm going to wait to see 4 emojis there. We have 1 right now. And let me know if you're encountering any issues. You shouldn't encounter any issues on a Ubuntu distribution, but it certainly might take a few minutes to install all of these. Anyway, moving on, what we're going to do afterwards is actually download. If you've already completed that, we're going to download the source code of GCC from the GCC main mirror, and then we're going to build. And as you can see, there actually is a Mac OS X section here, but we are going to ignore that and just do it from Linux distributions. So let's go to I'm trying to remember where I got the source code from. I believe it was the GNU main mirror. And this is what you have to watch out for, is the fact that these are not actually ordered by, we want to go to last modified and scroll all the way down to the bottom. Whatever's on top, it is sorted by name by default, which means all the way down on the bottom is not always the latest version. So we want to go to this. Oh, is this Binutils? We don't want Binutils. We want GCC. Where is my GCC link? Give it to me. The GNU main mirror. Oh, wait. I did click on the GNU main mirror. Let's see. And I think I want the tar.gz of the latest one. And then I'm going to open that up. I'm going to extract that from my downloads folder, and we are going to see I actually have it already, so I'm just going to move it over from my location. So if I do ls cd os, I think it's in source cd src ls. Yeah, so here are my installs of Binutils, right? And we also need the. Do I need both? Oh yeah, you need Binutils and GCC because we're also building the assembler because we need to actually assemble stuff since we're not just using the C compiler. All right, so moving on, let's actually take a look at what happens when we do this. So I'm actually going to move these over to our other thing. Let's see, gcc-10.0.tar.gz. Oh, we're going to move this. I think it's MV, it's not move. And then I'm going to move this to my other folder. But for you guys, you're just going to be downloading this from the internet, essentially. I will send over the link of I think I sent the link already, the GCC cross compiler page. You're going to be going to that page, and then you're going to be going down to this section right here, and we are going to get the GCC latest version. Where's the GNU main mirror? Here it is. Last modified. Scrolling all the way down, GCC 10.2. Okay, so we're going to be using this. And download the tar.gz, this one right here, for all of them. So we're going to be downloading the tar.gz for that. And then we're also going to be downloading the latest version of Binutils, which is this one right here. And I'll link the page that you can find that on. And back to actually building. I'm going to demonstrate how we're actually going to go about this. So I'm going to move this over to my thing, which is up to directories, and then I believe I call it osWorkshop. Yeah, so I'm going to move it into there, and I'm going to call this gcc-10.2.0.tar.gz, and we're going to do the same thing for our Binutils. Let's see. Binutils.tar.gz, good, and we'll finish this off with Binutils.2.35.1.tar.gz. I already have a tar.gz. There we go. Move it over. cd .. osWorkshop. ls, and now this is what you should have. You should have a directory. You probably should have created your own directory for this project, and then we're going to create. We have our 2 tar.gzs. So let me know once you have this set up, and we can continue from here. And if you're using WSL, you can get to your downloads by simply going into your file explorer and replacing all of the backslashes used in the Windows path with // and it's going to be in MMT-C instead of your C drive, essentially. Let me know if you have any issues if you're using WSL, because I actually can solve that since I'm using WSL. This isn't a true Ubuntu distribution. But if this was a true Ubuntu distribution, I would just download off of Firefox these files and then put them into my project directory, right? All right, so we have 2 people done with installing packages. Are the other 2 people encountering any issues installing packages? Let me know if you are, and I will give the assist. Anyway, do we want to... I guess we can continue with building from source, because building from source takes quite a bit. So for the 2 people who have already finished, we can try actually getting this on the road. So let's go back to actually taking a look at the guide of what we are doing. Now that we have our tars, we are actually going to unzip the source, right? And let's actually go down to building. Where's Linux? Do they not give us the actual thing? I swear they do. This note, by the way, about the Windows subsystem for Linux not working, this is maybe true. So if you're using WSL, try having it in your Linux directories, like your home directory with the tilde, rather than on a mount path, like your normal user home. I don't know if that's still a thing, since this was written like 3 years ago, but it very well may be. And and just to avoid that even being a potential issue, we can do that. Okay, so they want me to move that into a home source directory. I'm actually going to say about building stuff. Oh, okay, yes, I see what's going on here. So we should probably set a home directory. Right, I see what we're doing here. For the people who, let me create a new notification on Discord just so I can gauge where everyone's at. Let me know if you have the GCC and Binutils tar.gz downloaded. Okay, so what we're actually going to have to do now is going to be probably one of the most hellish parts of this process, which is going to actually be performing the cross compilation. So let's unzip these first. Unzip Binutils. Is it? I thought the command was unzip. It's totally unzip. Is it? It's not unzip. What do you use to undo tar.gzs? I used to know this off the top of my head. Look at that. I've just Googled it recently. Alright. Oh, that's right. You have to do... Okay, we're using the tar command. That's fun. Alright, so extract... What's the F option? Extract file... Is the F for file? I suppose so. Okay. In that case, well, what's V do? Does that give verbose? Oh, okay. In that case, let's be more fun and do verbose extraction. So I'm going to do... No, I want tar-xvf and the name of the file, gcc 10.2.tar.gz. And look at that. That's what I call an extraction. And yes, there's quite a lot of source code in these. You may not want to have it print everything to console. That might be slowing it down. Wow, it's still going. Is there anything fun in here? Probably not. I see that they act like literal Fortran code in here. All the test suites are in Fortran, apparently. Oh, there's MIPS. There's I386. That's what we're going to be using. Oh, we're onto ARM. I wish there was just a way we could do it exclusively for the processor that we wanted. Unfortunately, that is not a thing. As you can see, most of these source files are actually in C, which is interesting. The compiler itself is written in C. I guess we shouldn't be that surprised, though. Oh, now it's going much slower. template specs. Oh, now we're in G++, so we're even downloading all of the C++ stuff that we don't need. This is very unfortunate because we only need a very small amount of what's actually being extracted here, but we're basically forced to build the entire thing no matter what, which, so be it. Oh, we're in the change logs. I think this is this organized by an alphabetical order is a good question. I think it is. Oh, and just like that, we are done. So I'm now going to do the same thing for our other file. Now, did that extract everything here? No. It created this new directory, as you can see, which is the what was in that, right? And this is what we're going to be building out of. So now, let's get who's still installing packages? Is anyone suffering with installing packages? Like, are there any issues for anyone, out of curiosity? Or is it just slow? I'd like to know so we could figure out what's going on. For those of you who are following along, you can also share your screens so I can better keep track of where everyone's at as well, if you're so inclined to share your screen. And then I can do like the Discord video matrix to see what everyone's doing. Oh, that is not the Discord video matrix. Do I get the Discord video matrix? I know there's a thing. It's like the grid. Yes, yes. If you go to the grid, you can see other people who are streaming, and you can follow along with what they're doing. Yeah, you know what? I shouldn't have done. I'm gonna try extracting Binutils without logging with the V, and we'll see how long that takes. I honestly think that maybe the extraction took much longer because it wanted to print everything. So let's try extracting Binutils. Oh, you did it with XVF? Wow, you must have a very fast system then. Or you downloaded the wrong GCC. Okay, good, good. We want to make sure that everything's good. Oh, look, that extracted much faster. So now we have the source of Binutils and GCC right here. And now that we have the source of our Binutils, so once it's extracted, we can actually get to building. And the building is going to be the most hellish step, as I've previously stated. So, okay, they want us to basically set up a directory called opt cross, opt being operating system and cross being cross compiler. So they want us to, it doesn't really matter where we do this, but we can essentially do this wherever we want. So in my case, I'm in my osWorkshop folder. So I can just create a cross thing in here. Probably it would have been a better idea to move this into source first and have these be in like a source directory or something. But that doesn't really matter. All that matters is the fact that everything gets to where we want it to be. So I'm going to actually just create that directory that they want. So I'm going to make dir, I'm going to call it cross in my root here. And this is going to actually store the binaries for our cross compiler. And now we are going to go over to our build. And the first thing we're going to do is set up some global variables in our bash shell. And let's see. So they want this thing, the prefix. They want it to be basically the location of our cross compiler folder. So I am going to say that the location of our cross compiler folder is, I'm not going to do I'm going to just do tilde home, since that's where we are right now. And it's not an opt, it's in osWorkshop. And we're going to do it in the cross directory. And this is basically going to be the output of our thing, I think, right? Yes. Okay, so this is our output. And then our target is i686 elf. Now, what is i686 elf? That is the 32-bit elf executable format. And this is what we're going to be putting into our, this is the format that our operating system is going to come out in, the executable format. So, of course, you have, on Windows, you have exe files. And exe files are structured much differently from elf executable files, which are normally run on like Linux-based machines, right? So we're going to be using i686, which is a generic 32-bit, executable. And then we're going to be converting that into an ISO. And we're going to be using a linker script to specify how we actually want all of that to link together. So let's actually do the export. We are going to export target i6. So let's, oh crap, I removed my entire path that I just worked so hard to write. Let's re-export that. Export prefix equals tilde osWorkshop. And cross. So now we have access to prefix in the terminal. If I type $prefix, it's echo $prefix. There you go. It is osWorkshop cross, right? And now we are going to export our target, and that is going to stay the same on every operating system. Okay, good. So target's been exported. And finally, we're going to export this to the path. We're going to export our binaries to the path. Okay, so let's, so they're going to create a bin in cross for our binaries. So I'm going to put this here and prefix bin path. Yeah, so now this is on the path, right? So now what we're actually going to do is begin our struggle by building Binutils. So let's get suffering. The first thing they want us to do is change into our source directory. So we technically have a source directory share. And they want us to make a folder called build Binutils. And we're going to cd into build Binutils. And then this line right here is the configuration for Binutils. And then we're going to be running make to actually do the build of Binutils. And then we're going to run make install to install any of the trailing dependencies. And as you can see, we're passing our target in as we're building it. And that's really the reason that we're building it, is because we are building from source so that we have the option to target this platform, i686 ELF. Okay, so let's actually get down to business and start building it. So I do not want... Okay, so we're first going to make... I'm debating if I want to make a source folder, because I could make a source folder and make this even more painful. I'm going to go back and check out what I did for the other one when I did this the first time. So I do have a source folder. So if I cd into source, we're going to see that I have actual build folders. So I can just create the build folders right here, I guess. So I'm going to cd back. Now, let's actually create these folders. So make dir Binutils dash build. Okay, so now we have our Binutils build folder. And now what we can do is build into Binutils. So let's actually do that. So I'm going to cd into Binutils build, and this is what we're going to do first. So now I'm going to take my thing right here, the config file, and we're basically going to generate the config that needs to be run. So let me make this bigger so everyone can see this. Can I Control plus to make the terminal bigger? That is unfortunate because I would if I could. Can everyone see this? Basically, I'm just copying it. What we need to do, though, is edit this XYZ to actually be our Binutils version, which is 2.35.1. So I'm actually going to manually type that in. 2.35.1. All right. And now I'm going to hit enter. And this is going to create a config file that's going to be used during the build. Oh, what's this? Expected an absolute directory name. Oh, they don't want us to use the tilde. Okay, so I actually have to redo my tilde in that case, which is unfortunate. Where am I setting the tilde? Okay, so I actually do have to use $home. So be it. $home. All caps. Okay, let's try this instead. And there we go. So now we are creating the config. And as you can see, we have now we've generated a make file that we're going to be using. So if I ls here, we have our make file, and now we are just going to make. And now it is going to literally compile Binutils from its millions of lines of source code. And we're going to sit here and suffer while it does that. So while we sit here and suffer, I see that 2 people still have not finished installing all of the required dependencies. Is that because it's still installing or because you've given up? I would like to know if I can move on. Can I get positive or negative confirmation? Please. So the command to build, that's fine, Emily. Dan, so the command to build, what stage are you at right now? Do you want to share screen?
Sure, one sec.
Yeah, let's see what you got set up right now.
Okay, so I already did this command, by the way. So that's where I'm at. This thing
Alright.
just finished.
Let's see this stream.
Like,
So this is going to be a stream in a stream. So this is not going to be this is not going to be ideal. All right, Binutils, yeah, configure. You did that already.
Yeah, I did that already. So
so it's just make to build. Yeah. Since it generated the thing, now you just run make on the make file. If you ls, you can see what's in there right now. So if you ls, you see that now we have a make file in there. So we can just run make, and now it's going to build. You don't even have to type make file; it automatically goes to make file. Okay, just make, and now you are building Binutils, and this is probably going to take a solid 5 minutes.
All right, thank you.
All right, yeah, and then after this finishes compiling, then we are going to do GCC, which is going to take even longer to build. That's going to be a solid 10 minutes. So while that happens, while we're waiting on all of these to finish, I'm thinking maybe we should go over some code for the poor souls who aren't building from source right now and have absolutely nothing to do and are probably bored out of their mind watching us install and build GCC and Binutils from source. So the question is going to, on everyone's mind, is, well, what am I going to end up with at the end? So let's actually take a look at what we get at the very end of this process. What we end up getting is, if I cd into my home directory and now I ls in here, we actually see in cd os, ls, cd cross. So at the end of this process, we are going to have in our bin folder, ls-alt, all of these nice utilities. We're going to have all of these versions of GCC and AS, which is the assembler, and the linker, which are targeting the i686 architecture without an operating system. And that's really our goal here, is that we're basically building from source exclusively so we can get a compiler that targets our architecture that we want. So while we are still, and oh my god, they're still building Binutils. I don't remember Binutils taking as long as GCC, and the fact that it's still building is just kind of crazy to me. So once we have this is what we're actually going to be able to use to build our operating system. And that is going to be the main goal of building from source. So how we're actually going to do that, you ask? The build process is rather complex. So let me actually pull up what we have here. You know what, maybe I shouldn't go into actually building. I've wrote this very nice script that compiles all of the files for me, but this is, as you can see, we're actually using what we built here, right? So I have a compiler path and I have i86 elf AS, which is the assembler, and I'm using that to assemble assembly files, and then I'm using the GCC to compile the C files that are part of the operating system. And then I'm using GCC to link everything together, but this is actually calling the linker that we've generated, essentially. So let's go back and check on our build process, and look at that, it's done. So once we're done once it's done compiling Binutils, the next thing we have to do is actually do install. So now after I've compiled Binutils, I'm going to run make install. And this is going to finish up by installing any of the remaining dependencies. I'm not entirely sure what the install does in their make script, but they told us to run it, so we run it, and now everything should be fully set up. So now let's actually take a look at what we have here. So I'm going to cd back out, and as you can see now, we have, if we cd into cross, and now we ls, and then cd into bin, and ls, we actually have all of these utils that now exist on our system. So we have our assembler, essentially. This is the assembler that we're going to be using to build our operating system that's targeting this platform. So let's switch back. I'm going to ls ls and now we're going to do the exact same thing, except we're going to be building GCC this time. So as you can see, this has been utils, and now it's time to suffer and build GCC. So basically the same thing that we did before. They first want us to run this check right here to make sure that we have the assembler beforehand. So let's go back to our console right here, and let's switch back ls.cd ... and here is the root of our project. So now what we're going to do is create a GCC. Okay, so you know what? Okay, so technically this is our source folder. I'm using the source as our basically the root. I didn't create my own source for the source code and everything. I'm just using the root and then have cross as the folder that everything gets sent to. So let's actually make our you know what? Let's humor them and run the command to make sure that we have what they want in here. So I'm going to run this, and this is just going to tell us if we've developed the assembler. And they're mad at me because that's probably not the right path, and I probably did the path wrong. But I guarantee you, we have the thing. Is it just that it didn't get added to the path? Did they want me to add it to the path? We did that above. Prefix bin dir must be in the path. We did that above. Did I remove this from the path? This should still be in the path. I might have to reset this since home was different at the time, actually. Let's try that. Okay, yes. So that was the issue. So it wasn't that it didn't exist, it was just that the path was messed up. So yes, before we compile, run this check just to make sure that you've built your assembler correctly. And then it's time to build the actual thing. So let's make we'll start off by making the directory. Make dir mkdir build -gcc. And now we're going to switch into that, and we are going to start off by switching into that. Yeah, so cd build gcc ls. What happened to, why in the, oh, I called it Binutils build, not build gcc. And the other one was, okay, so I may have switched those back, I may have typed those backwards, but that's fine, doesn't matter. Now what we're going to do is the same thing we did before, right? We're going to actually compile this using, we're going to configure it now. And you're going to notice some really interesting options going in when we configure this. So, of course, we're sending in the target that we're targeting, which is our i686 ELF architecture without an operating system. And then you're also going to see this disable NLS, which I don't know what it does. We're going to enable C and C++ just in case we want to use C++ for operating system development, which can be fun in its own right. And it's even more fun when you remember that you don't actually have access to half the things in C++. So you're literally, if you use C++, you're going to be navigating around features that don't exist. Like the entire exception system doesn't exist, and the entire, like the new operator and everything, none of that exists either. You just have to ignore those language features if you're doing this in C++. And then, finally, the last one, we have without headers. And this is interesting because we don't want to have any headers available to us in GCC because most of the headers are dependent on operating system dependent code. So we're only going to be using freestanding headers, which we're always allowed to use no matter what, even if we include this here. But this is going to tell it, hey, we don't want any of your operating system dependent library functions. We just want the compiler to ignore those and not give us those. So yes, that's what we're doing. Next up, we are going to actually run this. So I apparently did not copy this. There we go. Copy, paste, run. Uh-oh, what don't they? Oh, because I hadn't changed the version number. So, right, we have to switch our version number over to 10.2.0. I hope you're all getting a good feel for what it's like to build stuff from source. And, all right, we have configured, and now we are going to run. We can't just run make now. They want us to run special commands to build GCC. So we're going to run these 4 make commands in a row. And the first thing we're going to do is make all GCC. And this is going to build the brunt of GCC for us. And once this is done, we will have a good and valid C compiler. But then we need to also build libgcc just for the remaining libraries that we are going to have access to, which are, I assume, the freestanding libraries, which I don't know why that's going to take such a long time, but it is. And it's going to be very painful. All right. In workshop text, let's see what everyone's at. So packages are still not installed for some people. For the other 2 people in here, react to this message if Binutils is done installing. Or you've started GCC. Well, that's mutually exclusive. I would hope you've done one. React if GCC, or not GCC, Binutils is built. And once Binutils is built, we will continue moving along. And of course, as you can see right now, we are building, at least on my end, I'm building GCC. And this is going to take probably like 10 minutes. GCC, as I recall, takes a lot longer, and you have to execute 4 make commands instead of just the 2 you previously had to do, even if 2 of these are installs. And the installs, compared to the build, it's much faster, because I actually don't know why, but it is. Oh, Brayden, do you need help? If you want to share screen, I can guide you along on how to get started for Binutils. Did you install Binutils? Like the file, not the actually building it. Like, did you install the source code from the download? You reacted to the thing. No, I reacted to the thing. Never mind. I thought my reaction was your reaction. Excellent, excellent. So once you have your source code downloaded in your directory for the OS, okay, you have both of them. Good, good, good. So once you have both of them, the next thing that you're going to want to do is to basically get all of this set up. So you're actually you're going to export your prefix, and your prefix is the directory of where we're going to be outputting the compiled binaries. So you're going to export these global variables, these path variables. So you're going to export prefix equals, and I recommend, honestly, if I link this, you can literally copy and paste this into whatever your terminal is. So I will paste this in, and you can go down here and literally copy and paste these 3 things into your terminal. And then we can begin the Let me know when you're done with that, and then we can begin installing Binutils. Let's take a look at the GCC progress just to see how we're doing. And as you can see, building GCC is no easy feat. We have all of this done, and they're running checks right now on things. And as you can see, we're getting compiler warnings going by. This is serious logging, considering, I mean, this is probably one of the most important programs in human history if you sit down and consider it for a moment. So I would hope that it would be this hard to build, but at the same time, it's incredible that we're able to just compile this from source on our own, right? And it is probably going to be done within, I want to say 3 minutes, but that may or may not be optimistic. We will see. How's everyone else doing? Has anyone given up yet? building an operating system is not an easy task. If you have not realized that already from the cross compiler, we are literally on step 1 of quite a few. If we go back to our page, where's our bare bones tutorial? Main page, bare bones. We are on step 1. And then what? But it's honestly harder to build your compiler and everything than it is to get all of this stuff set up. Once you have the compiler built, it feels like a major victory, and everything else after that to get the Hello World program set up is nowhere near as bad as the time and investment it takes to set up to build the cross compiler. Because once you build the cross compiler, you're in the clear to actually just get all of your program stuff out there. So let's go back to that is interesting. Kulog was one of the previous. I'm not actually sure if you need Kulog. I feel like they say that Kulog's optional. Yeah, it's optional. I don't think we need the optional things. It might automatic. I don't even know if I installed the optional thing. Let me check if I have Kulog. How do I check if I have a package? Apt check or something?
I don't think you do. It wasn't in the ones that you listed.
Okay, in that case, you don't need Kulog or ISL. We are clean. Yeah, my bad. I should have listed that those were optional. It says it on the site, but yeah, you should be fine to proceed without Kulog or ISL. Anyway, going back down, let's check in on our guy, and oh my god, he's still going, and he's appears to be frozen. Nope, there we go. All right, still going. While we wait for that, I almost feel like we should move on. We are at 9:05, and this depending on, I know quite a few of you are probably sitting here waiting to actually get on with the actual code for the operating system to get that up and running from scratch, right? So we will most certainly go over that next. So I might actually just build a new, since I've built all of this so far, I may as well just go the extra mile and create a new project as well, instead of showing off the project I have that already exists, but I am definitely going to be borrowing some code because the code is very nice. So, all right, let's go to, how's the progress here? GCC is still building, and I'm still suffering. Excellent. How's everyone else's installations going? For those of you who are working on installations, are you guys still doing the hour-long installations? Yeah. Okay, good. That's just want to make sure we're all on the same page. So, moving on. Why don't we actually, while we wait for this guy to finish, I'm gonna put this guy up on this. I kind of want to put him. You know what? I'll go put him on the other screen, and that way, I'll put him on the other screen with Discord so I can see when he's done, and when I have to execute the next make instruction in the sequence. So, let's actually assume that we've finished building our cross compilers, because this is going to take a very long time, and I don't want to hold everything up and hold everyone hostage here while we wait for this to finish. So while that happens, let's talk about booting old versus new. So I mentioned earlier that there was I just thought this was a fun little slide to point out here, is the fact that we have UEFI and we have BIOS, right? And so BIOS is more like the old model, right? This is like old board-dependent BIOSes, and they kind of wanted to move away from this model, which is why they've created this new standard UEFI. And UEFI, it's an acronym. It stands for, let's look up what UEFI stands for right now. UEFI, Unified Extensible Firmware Interface. Yes, so essentially it connects to the computer's firmware, and it's meant to eventually replace BIOS. So we are not actually going to deal with the UEFI today. We're just going to be focusing on the BIOS. But all you need to know is that basically they're trying to, eliminate the need for a master boot record and the bootloader and everything, and just go directly into the kernel. So it's also a faster booting time as well, I believe. is what they're going for here. And we're still building on this end. I see people typing in workshop text, which is very exciting because that means people have issues. While we wait, I kind of want to move on to what the state of the processor after boot, because this is a very exciting topic, because this is the first time that we actually get to know what the processor is doing and the state that it's in right as the operating system starts. On line 0 of our operating system, this is going to be the state of the computer. So once Braden finishes typing and I respond, okay. Yeah, so did you change directories into the new directory that you made for the build? Yes. So, oh, I know what it is, because you do tar.gz. After you've extracted, it shouldn't be a tar.gz anymore in the configure. Like the Binutils, this thing is a file, not a directory. You just want the file right there. Or not the file, the directory. And that's what you should have gotten if you ran tar extract on the zip file, essentially. And then the configure is in there. And that's what you're going to be working with. Does that make sense? Yes. You have to extract the source using the command tar-xf and then the file name. And you have to run that in the thing. And then do the same thing for GCC, and you should get out a folder named Binutils 235.1. And GCC is still building. You know, I probably should have had everyone build before the workshop, honestly, so we could have just focused during the workshop on actually writing the operating system code. But I do suppose that it was, especially considering how complex it is to get these built from source, I feel like it's better if everyone follows along. But I do apologize to everyone who came expecting us to be going over code and then spending 40 minutes waiting for everything to finish building the tools that we need to actually just build the operating system itself. But I am happy that for those of you who plan on doing this, not right now, but at a later date, or if you ever plan on building an operating system, you now have the tools at your disposal, and you know exactly how much suffering you have on your plate when you inevitably do attempt to build your own operating system. And as you can see, GCC still going here. I believe we're at. Does anyone know when I started doing this? I almost want to get like a count on how long we've been building GCC for right now. It's probably been at least 10 minutes. And it's still going, and this is just the first one. This is build all GCC. Next we have to build libcgcc, and then we have to do the 2 installs for GCC as well. So, enough complaining about GCC, even though I will inevitably complain more about GCC within the next 10 minutes. Dan is typing. Dan, did you finish? Spain, but the S is... Yeah. That's how I feel right now. It's exactly how I feel right now. All right, so you know what? Let's assume it's built, and now let's actually talk about what the... While we're waiting for everything to build, and please, by all means, if you're having build issues, for those of you that are actually building right now, at me, and I will hopefully be able to tell you exactly how to proceed. So, moving on to understanding the state of the processor after boot. And this is interesting, because since we're going to be using the grub bootloader and not writing our own bootloader, we are not rolling our own bootloader, we get the benefit of having the multi-boot standard apply for our operating system. So the multi-boot standard essentially guarantees how a bootloader leaves a processor for your operating system after the boot has taken place. And remember, we're not writing anything for the bootloader or the MBR. We're just writing the kernel code. So we're getting dumped off in the kernel, and the processor is going to immediately begin executing the instructions for our operating system here. And let's go take a look at the state of the processor as we are guaranteed it. I'm going to go with contents, and we are going to, this, by the way, for those of you who don't know, this is the multi-boot specification. Like, this is the official documentation for it. If anyone's interested in actually taking a look at that yourself, you can find it right here. And what we are interested in right now is the state of the PC, the state of the processor, directly after we've been dropped off right here. So after the operating system is loaded, we are loaded into 32-bit, and the machine is going to have the following state. Now, keep in mind, even on a 64-bit operating system, we're going to get dropped off in 32-bit mode. I'm not entirely sure if that's the same with UEFI, but the multi-boot standard guarantees you're going to be dropped off in 32-bit mode. And before I actually cover that, why don't I actually cover the different operating modes of your processor? So this is actually a very interesting topic for those of you who don't know about processor operating modes. So processor operating modes, your x86 processor, which I assume you're using, maybe you're using an ARM processor, but at least in the case of x86, x86 is so old. It's basically, I believe it's, let's see, it's probably 80s, so we're looking at least 30 years old at this point. And it has to maintain so much backwards compatibility that you can really see through the ages the evolution of x86, the x86 architecture, and what we have available to us. So x86 started off with 16-bit memory locations, essentially, right? So this was 16-bit memory address sizes. So in the beginning, there was real mode, and this was the only processor mode. And then, once we moved over to 32-bit operating systems, why did it change? I didn't tell it to change. Then, once we got into 32-bit operating systems, and I believe it was probably, was that late 90s, early 90s? Or maybe that was even the 2000s that we finally got off of, like MS-DOS, that was 16-bit, right? And then Windows moved into 32-bit, right? I could be crazy. I might be crazy. But I believe, I don't know my OS history as well as I would like to. But then we moved into our 32-bit operating systems, and behold, we now have protected mode and virtual 8086 mode. And the reason we have virtual 8086 mode is so that we can call real mode instructions in protected mode. Now, they call it protected mode, but really all protected mode is we are not able to call our BIOS interrupts. This is considered to be more safe than real mode. In real mode, we're able to call something called BIOS interrupts, which means we have direct access to the motherboard, essentially, and the BIOS to query system information and everything. But that is very dangerous, because you can also do stuff through the BIOS, like printing to the screen and connecting devices and everything, and you don't necessarily want users to have access to that. Or even your own kernel sometimes, in case, a virus infects your kernel code and gets into the kernel, you might not want to have the virus have access to calling hardware interrupts through the BIOS. So what we do instead is we go into protected mode. Respondus is also my favorite virus, Matthew. I agree. Respondus is 100% a virus. No questions asked. By the way, just a quick update. We're still compiling C on the first of 4 steps. Anyway, so there's a lot of different modes. So our thing is going to be in protected mode. Our entire operating system is going to take place in protected mode. And protected mode uses something called, you can either use segmentation or paging, and we are going to be using segmentation because paging is annoying and hard to explain. But I will get more into segmentation. You know what? I'm not even going to go into segmentation during this presentation because I do not need to. That is, I believe, those of you who were here for the presentation last night on the x86 programming language, we were talking about how segmentation, how you have to load the global descriptor table in assembly. And that is, we're actually defining segments for your code. But we're going to ignore that because we do not actually have to touch segmentation to get, or even care about segmentation to print things to the screen. Printing things to the screen you can do without any segmentation whatsoever. But it's useful to know about that segmentation. I suppose I probably should explain segmentation. Essentially, you just have regions of memory that are protected. They're either read-write, they can run in ring 0 or ring 3, which is either you have access to protected areas or you don't have access to protected areas, and you can execute some special instructions, like users are not able to access like normally the network interface and everything, which you can only do in ring 0, which is the kernel area. And basically you define these regions of memory in which assembly instructions are able to have higher privilege levels than other assembly instructions. And also, if you want read-only data, you can specify segments that are read-only. And that's what protected mode is. It offers a lot more security features, essentially, than real mode or virtual x86 mode. But you do sometimes want to drop down into virtual x86 mode just to basically call BIOS interrupts. And we're actually going to see that we do that. We're not actually going to do that, but we would need to do that if we wanted a windowing system, which we don't. We do not care about a windowing system right now. We don't actually want to set pixels. We just want to set characters on the screen, which, lucky us, we get dropped into default VGA text mode, and we're able to directly write things to the screen. And we don't have to care about setting up, going into virtual 8086 mode to set up our frame buffer or anything. So we're not going to be using virtual 8086 mode. But also, I should probably just point out that all modern operating systems are in long 64-bit mode for 64-bit operating systems. We are not going to be touching this, and this is going to be, for those of you who end up developing, if you ever find yourself developing a 64-bit operating system, good luck, because this is slightly more annoying, and it does not translate well to protected mode, writing an operating system for protected mode in 32-bit. But you can also see that a subset of long mode is compatibility mode, which lets you run 32-bit and 16-bit applications, which Windows does not seem to let you do because I'm not allowed to run my 16-bit applications on my Windows computer. They complain at me if I try. Anyway, enough about complaining about all of the different processor modes. Let's go back to the state that we are left in right out of boot. So this is what grub guarantees they are dropping us into. So they guarantee all of these different register values in all of the registers, right? So the first register, EAX, has this magic number. So this means that if EAX is in this first register, that means that we know our operating system has been loaded by a multi-boot compliant bootloader, as in we're basically guaranteed that all of this is also true. So this is like the if statement. If you wanted to put an if statement and check, oh, does EAX store the... For those of you who don't know about registers, I hope you all know about registers because we went over this last night during the x86 workshop. Registers are just very small, fast memory locations on the processor directly that we have access to in our assembly instructions. You're actually going to see that in the operating system that I have here. If we go into source and the boot sequence right here, one of the first things we do is move EBP into this multi-boot table location. Into this, where is it? Yeah, right here, multi-boot table, this thing right here. We're moving the address of what's stored in EBP, this address of the multi-boot table, into this location right here in the data section. And the reason we're doing that is because if we see right here, the second thing is the EBP register contains a 32-bit address of a multi-boot information structure. And this is extraordinarily useful. Now let's talk about why this is extraordinarily useful. So when grub runs, one of the things that it does is generate this giant structure containing all of the device information. And what's important about this is the fact that we don't have access to this structure. We're not able to get this normally in protected mode because when, okay, let me, I can show this off actually. Let's go to, there's actually a whole page on this about finding out what memory is taken. And I'm just struggling to remember what it's called. Grub memory. Let's see if we get anything here. I want to figure out, what was it called? I know it was a thing. I'll figure it out later. I'll remember in due time. It's not important. But essentially, the way that grub gets this is grub, when your computer boots up, you're starting off in 16-bit real mode. But by the time we're done, the multi-boot specification guarantees that we are getting dropped off in 32-bit mode. And we can see that right here in the control register. that PG is cleared and PE must be set, which means if we take a look at these actual things right here, if we look at this, well, what's PE? Protected mode, PE is protected mode enabled, which means grub, despite starting off in 16-bit mode initially in real mode, grub then puts us into protected mode. And once we're in protected mode, we do not have access to our BIOS interrupts. And normally, the way that we get a lot of this info is by querying the BIOS and saying, hey, what does the system have? What are my PCIe connections? What's in RAM? Are there any memory map devices in RAM? And you do that through these interrupts that you can only call in real mode. So what grub does for us, which is very nice, is they get all of that information for us while the processor is still in real mode, and then they send us over to protected mode. And if we actually go back to, where were we? The multi-boot specification, we see, yeah, so bit CR0 or bit 0 protected enabled, so we're in protected mode, but they are giving us in EBP the address of the multi-boot information structure. If we take a look at the multi-boot information structure, we get access to all of this useful information that we might want to use while setting up our system. So for example, let's take a look at what we can find in here. So we get this memory map, and the memory map is very useful. This is one of the first things that this was primarily the reason I'm using this, is because not all memory addresses are legal to use. So when we think about memory in a traditional sense, on a 32-bit operating system, if you have 4 gigs of RAM, you have addresses that go from 0 to basically 4 gigs, right? But you're not, and you would think that, oh, it's my operating system, I get to manage all of that. Not exactly, because the first thing that happens, keep in mind, the bootloader gets loaded into RAM and it starts executing the bootloader. But then after the bootloader is loaded in, it's loading your operating system into memory as well at a certain address. So what we're doing, especially in, I'm going to jump ahead a bit here and just show off what we have here. In our linker script, we're telling it to start at 1 megabyte right here. Or is it a megabyte? I'm not entirely sure what it is. GCC finished? Did my old GCC finish? Oh god, it finished. I wonder how long it's been finished for. Okay, in that case, we're going to go back to building the cross compiler. How's everyone else doing for builds? Binutils or anything? I'm going to, next, after you make all GCC finishes, we have to run all target libgcc, and we're going to build that next. All right, all GCC still. Good. Does this actually go really fast? I feel like this one goes really fast. Not make all target lib. Let's try it. All right, and here we go. That almost looks like it's done, but I'm suspicious. So I'm going to move this over to the side. The mistake was covering it up behind. Okay, so now let's go back to what we were talking about before. So I was discussing the state of the processor after we get dropped off. So all of them are finished. Okay, congratulations, Dan. You officially have the tools necessary to build your own operating system from scratch. With that, okay. And there'll be a few more things, but I think you installed all the grub packages, which convert our ELF into an ISO that we can load into VirtualBox. So let's take a look. Oh, that finished as well. That actually goes really fast. So if we go here, now I'm going to do make install GCC. Yeah, these ones are much faster than the actual compiling of the entirety of GCC, which was make all GCC. That's the one that takes a really long time. So now we have access to our actual compiler, and we can access it through, Dan, you're going to be able to run it through this. And I'm actually going to do this in VS Code later when we actually go into programming the operating system. But right now, I just want to make sure everyone understands what the state of the processor is before we actually go in and see any code, because this is very important, and this really influences the assembly script that we are going to be using. So again, I just wanted to briefly mention the fact that grub gives us all of this useful information, so we don't have to query the hardware ourselves. The bootloader grub is handing us all of this information. Now, keep in mind, if we weren't using grub and we wanted to write our own bootloader, we would have to get all of the information we needed ourselves in real mode by calling interrupts and getting that from the BIOS. But thank God we do not have to do that, and grub gives us all of the information we need. And of course, some of the most important things that they're throwing at us is, here they're listing everything. The number one thing that I find extraordinarily useful is where is it? I know it's here. Flags 6. This right here, this tells you what memory is being used and what's like hardware memory mapped and what memory is free. And with that, we're allowed to actually figure out what our segmentation addresses are. And something that's really interesting that you may not know about is the fact that there's various areas of memory, and this is especially common on like Game Boys and stuff, where regions of memory will be reserved for buffers for hardware devices. And this is a perfect example because we're actually going to be jumping into this next, that what's actually going on is, if we go to the actual, that's not the right project. I'm Xing out of that. I'm going to save it and then X out. Okay, so this is the operating system, right? So if we actually take a look in here, we are, what was I going on about? In the boot, where did I put boot? Boot, here we are. I completely lost my train of thought. Was I going over memory? Oh, yes, that's what I was going over. So we're actually going to be using something like this, but you see here I'm casting a random number to a pointer in memory. So the reason that we're doing this is because what's actually going on is that we are guaranteed that this address is the start of the frame buffer in memory. And it feels like incredibly weird to be doing this, but the hardware guarantees that this is the start of our frame buffer in just normal RAM. But that means that we don't have normal access to this RAM. We can't like reserve this RAM and use this for our own programs, because if we tried to write memory in here, we would be writing to the frame buffer for the console. And we don't want to be writing to the frame buffer for the console with just like our normal programs and everything, because it's supposed to store character data, of course. So what GCC or what grub is doing is they're actually passing in this structure, this memory map that tells us what sections of memory are reserved for memory map devices and what's free for us to use for our operating system. And when we want to develop our own stack and everything, and all of our own operating system code and all of the user space code that will inevitably be written, we need to know what areas are free for that. And of course, we're not even going to be touching on that tonight, but just keep in mind that when you're really developing an operating system, it's very important to know what areas of memory are memory mapped and what isn't memory mapped to a hardware device, and what we have free for our own personal use. So we are going to basically ignore all of this for now, but I think it's very interesting to know that grub actually provides all of this information for us. So if we go back to what the state of the operating system is, I'm almost done with this. What's actually interesting is when we enter protected mode, grub already sets up a global descriptor table for us with all of this, a bunch of different segments. However, what's interesting is the fact that we are not supposed to use the global descriptor table grub sets up for us, and we're supposed to completely overwrite that. And the reason for that is because I don't think they guarantee the location of it, and they want you to basically write your own. And the reason that they do that is because they want to set up interrupts and everything for grub's program. Yes, Dan. Let's no such file directive. Well, is it in that path? Do you still have all of your variables and everything set? Yes? Okay, this is interesting. In that case, let's can you do a screen share real fast? I'm curious about what the issue is. If everything's worked. I don't even remember what I just built. All right, let's take a look at Dan's stream real quick.
All right, so basically whenever I run this command, it's from the documentation. Well,
here. I see the issue already. It's because you're doing opt instead of the name of your folder. It's IEEE_OS cross, not opt cross.
Wait, oh. Okay, there we go.
Try that.
Okay.
Beautiful, beautiful. You got everything working out, and that's perfect. All right, so let's let's move on a bit. Does anyone else, how's everyone doing on their GCC builds for everyone else who's building GCC? I know all GCC takes like half an hour. I think I can't even remember if I did the final make yet. Still building away. Yeah. I'm not surprised at all. This is true software. I think I did install GCC. I think this is my last command, and after this, I'll be done. Oh wait, is this it? Is everything done? Let's check. Home opt cross target. Home opt bin target GCC, and keep in mind we're not there. I'm in osWorkshop, and look at that. We now have a i686 ELF GCC compiler. And this is exactly what we want. And this is going to be great because from here, we're actually going to be able to build our project. So let's get to it. Let's go back to, I want to just finish talking about the multi-boot specification because again, this is important because this lets us know the state that the processor is in when we begin building. So back to, is this being recorded? June, can I get confirmation? I believe June is recording it. Pretty sure. Emily, where are you at in the process? Are you? I assume you probably missed the entire thing about downloading Binutils and everything, which was that's a big step right there. Yeah. So you download. Did you unzip it? You have to unzip Binutils and GCC. And then, okay, if it's unzipped, then the actual building process is really straightforward because it's documented right here. So the first thing you have to do is you have to set up this preparation, right? So you're exporting basically the location. This is going to be the location of your build. So the first thing you're going to want to do is actually create a cross directory in your root. And as you can see, if we cd into the root of my build project right here and I do ls, we actually see my cross directory in here, right? I have my zips, I have my extracted things, and then I've created these other build directories essentially to store all of our make files in, right? So then what you're going to want to do is essentially put, where'd my terminal go? So many windows, I keep getting confused. Yes, so you're creating a cross right here. And good work, June, by the way, with timestamps. I love the timestamps on the YouTube videos. They're very helpful. By the way, if anyone ever wants to watch my workshops back, always watch my workshops back at ×2 speed because I feel like I sound much better when talking at ×2 speed. Otherwise, I feel like I'm way too slow. Anyway, yeah, so after you've extracted your Binutils, so you should have basically this right here in your root directory, right? And then what you're going to want to do is make dir cross. So once you make this directory cross, it's just going to be an empty directory at first. But then what you're going to want to do is export that your prefix is home and then the root of your project. So in my case, it's going to be export prefix equals, I did this before, home opt cross. It's not going to be home opt cross. It's going to basically be home and then whatever the root of your project is. So in my case, it's ampersand, or not ampersand, tilde osWorkshop, which is home osWorkshop. So this is home osWorkshop. And then /cross. And this is where the OS build is going to end up, essentially, right? And then what you're going to do is you're going to set the target. You can just copy this one line for line. And you can also copy this line for line. And what this is doing is this is telling the Binutils build and GCC build what platform we're targeting. And then the path is essentially just letting us know that we want this on our path so we have direct access after we build it. So, for example, I actually can show this off that I have perfect. I actually think I did that already, right? It's this command right here. Because we've put it on the path, we should actually just be able to run it like this. Yeah, so because we put it on the path, we have the ability to run target GCC -- version. But once you actually, once you have all of these exported, to actually get rolling, since we didn't use a source directory, normally we could have thrown all of these zips and everything in a source directory. We didn't do that. We don't care about that. So you're just going to want to follow this basically line for line. You're going to make a directory called build binutils. You're going to go into it, And then you're going to run this configuration command. And you're just going to replace XYZ with the current version of Binutils that you downloaded. So let me know if you have any issues doing that. And then you run make and make install, and that's going to be the build for Binutils, essentially. So now that that's all cleared up, let's switch back to the machine state and just finish talking about the machine state before we move on to what we're actually doing. So finally, I'm not gonna discuss about the segment registers. Just know that the segment registers have to be the entire width because we want to have access to everything basically when we're setting it up, and that's why grub sets these from 0 to FFF and give us a read execute code segment there, essentially. All right. So next up, we have CS, and then DS basically gets the same thing, a segment from 0 to the memory limit. And then the A20 gate, I actually don't know what the A20 gate is, so I'm going to ignore that. CR0, again, this is the control register. CR0 is control register 0. And this basically says paging is disabled, and paging is it's a processor feature on modern x86 processors. We are not going to be using paging. We do not care about this, and it's off by default, so that's good, right? And then protected mode, we are in 32-bit operating mode, essentially, when we enter. And then finally, eFlags, the VM bit is going to be cleared, and the IF bit is going to be set. This doesn't matter to us. We're not going to actually be looking at the eFlags. And then finally, this is the important part, is the fact that the OS image we need to create our own stack immediately. And here's why creating our own stack is so important, is because if we want to run C code, C expects us to have a stack set up, but a stack is not set up by default. The stack doesn't just exist. The stack just doesn't exist in x86 programs. You actually have to tell it, oh, I need the stack set up, by setting the stack pointer and the base pointer, essentially. And that's what they're basically depending on. And of course, C is going to move the base pointer immediately, right? So we don't actually have to worry about that. If we take a look in the boot.s, what we're actually doing here is moving the stack pointer to the top of the stack, which we're storing in this uninitialized BSS data section in our OS. And we're only giving the stack, our initial stack for our kernel, 16 kilobytes. So let's actually talk about getting everything set up. Now, this is going to look intimidating at first, I'm sure, but it's time to actually go into the code. So let's go into the bare bones tutorial and take a look at this. So this is the Bootstrap assembly, essentially, that they've set up. This is going to be what calls your main function. And they've added all of these really complex comments and everything. I feel like this is overkill for what for explaining what we're doing. Okay, so all you need to know, essentially, everything up here, all of this stuff right here, this is black magic, so grub can detect our operating system. Grub needs to know where our operating system is on the disk, and I'm pretty sure this is how it identifies it. We put this magic number that lets the bootloader go through the disk until it hits this number, and once it hits this number, it says, oh, okay, everything after this is our multi-boot compliant operating system. And we're also adding all of this other fancy stuff to it. But essentially, we're just putting all of this is just parameters and everything that we're sending to grub to tell it, hey, I'm a multi-boot compliant operating system. Notice me, senpai. Like, that's all that's going on here. And that's in this multi-boot section. For those of you who don't know what a section is in assembly, it's basically just a way of compartmentalizing different little binary sections. And these are all assembly directives. So this long here says, oh, put a 32-bit number for our magic number. This is declaring variables, this dot set. This is basically just saying align equals that, meminfo equals that, flags equals that, magic equals that, checksum equals that. This is our directives to set variables in assembly. So we don't really care about the variables, but what we do, this entire section, it's kind of just black magic. I don't fully understand how this works myself. Like, I don't know what any of this is. I don't know what, like, why it has to be this number, why we need a checksum. But this is what grub says we need. So as far as I'm concerned, it works. And that's how they're finding our operating system on the disk, right? So now that we know how they find our operating system on the disk, we actually need stuff to run in our operating system. And what's actually going to be running on our operating system is the .text section. And the .text section is the actual assembly code that's going to be running when our operating system is called. So the first thing that happens when our operating system is called is the start function gets called for our operating system. And the start function, it's basically, you can think of this as our main, right? And what's funny is this doesn't actually have to be called _start. We're actually specifying that in our linker script. We're telling it that the entry point of our executable is going to be this _start. And I'll go over the linker script a bit more later. But all you need to know is that all of those sections from our operating system file, what we're actually doing with these is basically splitting them up and then throwing them into a raw binary based on an ELF binary based on their names, essentially. So the .text section, we're putting that right here. This instruction right here in the linker script says, oh, skip over the first the first MB essentially of memory, and then we have access to, then we're going to start loading our instructions into memory. The first thing we do, though, note the first thing we do is the multi-boot header. So the first thing that goes in here is the multi-boot section, and then we follow up the multi-boot section with our text section, which is our assembly language instructions that start going. So the multi-boot section says, oh, okay, this is our multi-boot compliant operating system. Now everything after this, text, RO data, data, common, BSS, all of these other sections are put after it. And it now knows that this is a multi-boot compliant operating system in the data following it on the hard drive. Now, just keep in mind that this is all on the hard drive, but the bootloader is going to be putting this, translating this from the hard drive into RAM. And this here is telling it, don't put anything in the first megabyte of RAM, because that is where hardware memory map devices are, as previously discussed here, where this is under the first megabyte, and this is a hardware memory map device, and we do not want to touch this because we don't want to write our operating system into the frame buffer, essentially. We want it in free memory, and that's why we're jumping 1 megabyte in our linker script. So back to the actual boot. Let's actually talk about the assembly instructions that are getting executed the second we start it. Now, this is the entire assembly wrapper for our operating system. Well, all we're doing is we're saying the first thing we want to do in the BSS section, we're setting up the stack and we're aligning it on a 16-bit boundary. That doesn't really matter, but, well, it does matter, but we don't need to, I don't need to explain why that happens. That should be obvious. Well, it shouldn't be obvious, but it's basically we just want it so, you know, we're not calling bytes on, we're not calling things on like a weird bit boundary. We're actually just, we have everything aligned on a 16-bit boundary. So essentially everything, all of our addresses are a multiple of 16. That's what that means. And if it's not, it pushes it up. So all of our the next addresses are multiples of 16. So what we're actually doing here is we're declaring, you can think of this as if we're kind of declaring a variable. We have this label here in memory in the BSS section saying, okay, this is the bottom of the stack. And then we say skip 16 kilobytes, and then we declare the stack top. And essentially, these labels are saying, okay, so in memory, in the BSS section, we have the bottom, and then we're jumping this many bytes, and then we're declaring this a new label to the top. And you can kind of think of these labels as pointers to the memory locations if you want in memory. And keep in mind that the BSS section is actually at the end of our program. So this is going to happen after the text section. If we look at the linker script, what's going on here, again, the first thing that gets put in, the multi-boot header, the text header, and then the data, and then finally at the very end, our stack is down here, following everything. And if we want to visualize that, I can open up MS Paint and see what's actually going on here. All of our sections get split up. So the first thing that our linker script is saying is, okay, at section 1, so let's say we have 0. Where is the brush? I have the brush, right? Okay, so here's 0 in RAM. This is literally 0 in RAM, like the null pointer and everything. That's the base of RAM. And then up here you have the max of RAM. This is 0xF, then that's 8 Fs, essentially, right? That's the 32-bit limit. So that's the bottom of RAM. So up here, essentially what we're saying is, okay, we're going to skip 1 megabyte. And so now we are at, this is 1 MIB into RAM. And the reason we're skipping 1 MIB is because hardware mapped addresses are under here, and we do not want to touch these hardware mapped addresses. We do not want to be writing our operating system memory into hardware mapped addresses. And now, after that, we're saying, okay, the first thing that we're going to put in memory here is our multi-boot header. And we don't know how big the multi-boot header is going to be, but that's going to be right here. So this is going to be our multi-boot section in memory. Multi, I should probably just get the type tool. Multi-boot, easy. Okay, so the next thing that we're going to have in memory is the text. So that's actually going to be the program code for our operating system. So let me pull out the brush, and this is code. And this is the .txt, .text. And for those of you following along, I will be giving you the code so we can use this next. So there's our .text. And then after the text, we have our read-only data. I don't actually have a read-only data section, so this doesn't matter, doesn't exist. So next what it's going to do, it's going to skip over that, and it's going to go to our data section. And we actually only have one thing in our data section, so it's going to be like 4 bytes. If we actually take a look at the boot section, I have a data section here, and the data section contains this one thing. It contains 32 bits for the multi-boot table address, and that's it. We don't do anything else with that. So if we go back into our MS Paint diagram, we do have a data section, but we're not using it. Data, well, it's very small and it doesn't matter. But the next thing that we have is if we put our, the next thing we have in, where's the linker script? Linker script. Here it is. So in the linker script, the next thing we see is we have common, and we're ignoring common. And we're going to just take a look at BSS in memory next. So here is, so data is actually this, text is this. And keep in mind that these are pointers to the beginning location. So multi-boot is actually that, text is that, data is that, and that means that finally the stack, as we would call it, the memory that we have access to, is all of this right here. This is data minus 16 KB. Data, and then this is minus 16 KB, minus 16 KB essentially. So this, the distance between start and the bottom is 16 KB. And that's not a lot of memory for the stack, but ideally, if we wanted to run real programs or get more memory, this is just the stack that we're using to initialize our kernel. If we were writing a real operating system, we would give it a lot more memory, and we would be using our memory manager and everything to figure out where we're going to put the stack and everything. So let's go back and take a look at our boot script. So the first thing that we do is we declare the stack, and what we're saying is that we're moving the stack pointer. The stack pointer is not guaranteed to be set by the multi-boot standard. If we look at the multi-boot standard, ESP says the OS image must create its own stack as soon as it needs one. And to run a C program, to call a C method, and kernel init is a C method, when C compiles, you are guaranteed to give, C expects a stack to already be set up. So the first thing we have to do is set up our stack before we can call a C method. And that's exactly what we're doing when we say move ESP to stack top. This is quite literally, if we look at our MS Paint drawing, this is stack top right here. This is stack top, and down here we have stack bottom right here. Stack bottom is, where is my, I just want to draw. And this is stack bottom. So essentially, we are saying, okay, move the ESP to stack top, the address of stack top. So now our ESP register, which is the pointer to the top of the stack, is at this location. And that's exactly what we want. And now that we've set that up, we are able to call a C function, because a C function expects that ESP is already going to be set up. Anyway, the next thing that we're going to do is we're going to, this instruction right here, EBP is going to be modified by whatever C function we call. So I want to make sure, if you remember from the multi-boot standard, EBP is guaranteed to be set to the multi-boot information structure. So I want to preserve that structure at all costs, because EBP is going to be modified almost immediately in whatever C function we call. So to prevent EBP from being modified and losing the value of that multi-boot information structure forever, I store it first into the location of multi-boot table, which is this variable right here, which is just a 32-bit number. Since this is a 32-bit operating system and EBP is a 32-bit register, this move instruction works perfectly. So we're moving EBP into the multi-boot table. The next thing that we're going to do is actually, finally, we're going to get around to calling our C functions. So I have two C functions. I have kernel init and kernel main. In our case, we are not going to be using kernel init. We are exclusively going to be using kernel main. I have kernel init and kernel main split up for no particular reason. Honestly, they should probably be one function. But anyway, yeah. So we're calling these C functions. And the reason we can call these C functions is because behind the scenes, of course, C compiles to assembly. So if I actually take a look at my kernel.c file right here, I have kernel init and kernel main as C functions right here. But again, so this multi-boot save data permanently stores the multi-boot structure, and then GTT init is setting up a global descriptor table. That doesn't do anything for us. We don't care about either of these right now because we are not using that multi-boot information, and we're not trying to get keyboard input or anything, so we don't need a global descriptor table or an interrupt descriptor table. We're able to completely ignore that and just move on. So kernel main, let's actually take a look at what kernel main is going to do. So we actually have to write our own terminal methods and everything to print stuff out, but thankfully that's going to be the least of our issues. And then finally, after we exit kernel main, we basically just want to freeze the processor forever and not do anything. So we call this CLI instruction, and this disables interrupts. So I'm not really going to talk about interrupts. All you need to know is that halt right here, the halt instruction freezes the processor unless there's an interrupt. And if there is an interrupt, this halt unfreezes. So the reason we do this is because we want to freeze the computer permanently after we print the thing out, and we don't want anything else to happen. So that's why we're disabling interrupts, so we can't unhalt this. But then in the off case that somehow some weird thing happens, we get errors and we do unhalt, then we jump back around and halt again forever. And that way we're never going into memory that we're not using, and this is basically the death loop, if you will. So once kernel main finishes, and ideally you should never leave kernel main. Ideally we would have our kernel event loop inside of kernel main doing a bunch of magic in there, but we are not going to worry about that. We are basically, once it prints out, we death loop it and it's done. The operating system has finished its goal. And then finally, this thing down here is basically we are declaring the size of the, I'm not entirely sure what this directive is doing, to be completely honest. All I know is that they use it, so we're going to use it too. If we actually read this, set the size of the start symbol to the current location minus its start. What? Minus the current location minus its start. This is useful when debugging or when you implement call tracing. I'll take their word for it. Anyway, so if we actually, so the first thing we're going to do is actually just get this file set up for everyone. So for those of you who have been following along, I kind of doubt you've typed this all out yourself, but I am going to basically create a new project here. I'm going to open my folder in WSL. If you have like Notepad or plus or anything, you can do this in whatever editor you want, as long as you're able to access WSL from command line and you can compile all of this, you're basically fine. So I'm just gonna new window this, and we're basically gonna create a new project here and basically just reuse some of that code. So let's go new file. No, you know what? Open folder. Program IEEE. I'm going to call this new folder the OS Workshop. And let's go into OS Workshop. So if you're running on a fully Ubuntu virtual machine and you're following along with this, you can literally use any text editor you want to do this, as long as you have access to the compiler that we just developed, right? So the first thing that we're going to want to do is create our boot script that we just saw. So I'm going to take this and I'm going to modify what I wrote. And what I've written is actually just, if you look at it, it's literally just this without comments. We're calling kernel main and everything. I'm going to actually just copy their version, and we're going to remove all the comments just to make it smaller, because I don't like the fact that they've added a gazillion comments. So we're going to call this, this isn't really the boot. This is the first thing that gets called by when our operating system starts off. So let's remove all of this, and they didn't name it Deathloop. I like the name Deathloop more, so I'm going to change that to Deathloop because that's really what it is. And I feel like if we don't call it Deathloop, we lose the appreciation for what it's actually doing. This is the Deathloop. Okay, so let's remove all of these comments. We're not setting up anything here. Yada, yada, yada. Okay, so now, as you can see, we have a very nice little assembly wrapper around when we're calling our C function. So let's get rid of all of these comments, and this is welcome to the bootloader. Okay, so also this has to have an extra line after it, and now I'm going to take this file and distribute this to everyone at the workshop. So pull this up. Hang on, where is my... How am I going to distribute this? I guess I can just distribute the text. That's fine. Rather than uploading the file to Discord, you can copy and paste this. Let's see. ASM. No? Doesn't like that? Okay. That's unfortunate. Well, that is the assembly code in the thing right now there. So you can copy and paste that into a file, and probably I would recommend calling it boot.s. Let's see what else we have. So the next step that we're going to take is to actually write the C program. So for those of you who's following along with everything that we've done up to this point, because at the moment I've basically just been going over what's in this file. So how many people have finished the installation for everything and have everything set up? Can I get a show of hands in the workshop text? Let's do a thing. Dan's still up to date. Wow. Still on all GCC. Oh my god. Okay, that's fine. Once all GCC finishes, it's pretty easy. Again, much easier to just set this all up. Right? So does anyone have any questions about what's in this file, by the way? Because I know assembly is very intimidating to some people the first time they see it, but when you really just look at it on an instruction for instruction level, it's not that scary at all. This is just ESP equals stack top. This is just calling our C function. This is disabling interrupts to let us go into this death spiral right here. And all of the rest of these are just directives about setting up the stack and everything. So it shouldn't be that scary to people. But if you have any questions about it that I can answer, feel free. Again, a lot of this, like I couldn't tell you in depth what all of this black magic going on up here for the grub header is, but at least it makes sense. The general concept of why we need it makes sense, right? So that's what we're going to be using. Anyway, so the next thing that we're going to do is now we have our boot.s file all set up. So now that we have boot.s all set up, the next thing that we're going to want to go ahead and do is actually set up our kernel. And now this is very interesting, right? So they have all of this code here to set up their kernel. So what I'm actually going to do is now go into actually what we want in our kernel. Because all we want our kernel to do, we want a very simple kernel. All we want to do is print out hello world, okay? So this is where things get really fun, because we get dropped off in VGA text mode. And as previously mentioned, VGA is memory mapped to an address in that memory space less than 1 megabyte. And that address is 0xb80000. So anything we write to this is the frame buffer, and that will show up on the screen. And it's just a completely arbitrary random address in that area, right? Now, what's interesting is the actual format that we have to write things to the screen in. So each one of these, every byte in here is basically every 16 bits is a character. So every short is basically a character. Now, here's how these 16 bits are broken down based on what character we want to display. So rest in peace, Daniel. Goodbye. We will miss you. Very fun. Thank you, Dan. Have a good, nice night.
Peace, good night.
Okay, so back to what we were discussing previously. This also means, guess what this means? It means no one else is actually working at the current level, so I'll be able to get through the end of this much faster. Probably only going to be like another 15, 16 minutes or so. Okay, so essentially what we're doing, we are split. Okay, so yes, characters are 16 bits, which you might be like, oh, okay, I thought characters were normally 8 bits, but we have to take into account the fact that VGA has an attribute preceding every single character. And the attribute gives you the ability to change the foreground color of the character, the background color of the character, and whether or not the character is blinking. There's a special blink flag to indicate whether we're blinking or not. I actually don't know if we have access to this in our operating system. That you might have to set a special flag for that in a control register somewhere. This might also just be a fourth background color bit, as they say here in note 1. But essentially, then the code point is the actual character that's being displayed, and you can just think of this as the normal VGA ASCII characters. And actually, I think I have a good resource for that. These are the 156, or the actual ASCII alphabet. Note that the ASCII alphabet for code points is not the same as ASCII, and while it does line up with ASCII, as you can see, the ASCII characters are in their normal places. In the places where there normally aren't ASCII characters, like all the control sequence characters, they actually map to their own stuff. They map to all of these emojis and everything, and all of like these weird like line breaks and everything over here, right? So that is the code point. So like, for example, this is 0, 1, 2, 3, and just down the line up until, I believe this is 256. This might be, yeah, 256. So you have access to all of these, weird other characters. And the reason they had these was basically to create these text UI interfaces back in the olden days when there was only VGA text mode. So basically, we're able to select bits out of here to choose what character to display, but this maps up to ASCII characters and numbers and letters, so that still all works. But as you can see, we also have the entire Greek alphabet, and we have these weird UI things. Anyway, so now that we know how to display a character and what we're actually doing, the way that we're actually going to display this is we're going to write 16-bit. We're going to write to this address in 16-bit increments. So the way we can do this is by casting this as a pointer and then basically just writing to that location. So they decided in their infinite wisdom that it would be fun to set up a terminal program in the bare bones interface. This is too complex for us. We don't care about this at all. We are quite literally just going to do this raw and write to that memory location. Since we're only writing one line, we don't actually have to care about like writing a terminal system where it prints to the next line and you can push stuff to it. If you wanted to do a terminal, you actually have to write the terminal yourself. You are not able to just do printf and have it print out on a new line. And you don't even get the, like if you print a new line character, it's not actually printing the new line character. You actually have to do the new line yourself and skip to the location in memory where you're going to be writing the new line character. Yeah, I'm very sad as well, Brayden, there's no standard galactic alphabet there. That would be much more enjoyable. However, there is some VGA black magic you can use to change your code points. I just don't know how to do that yet, but I think it would be very interesting if I could figure out how to get that rolling. But I know there is a way to do it, and I'm sure it involves writing to a separate special memory address. So let's actually take a look at writing a string to the console and to that magic memory location. So I'm going to switch over to a very small utility I wrote in my old operating system that does, where is it? Boot.s, which one is it? The real one. So this alert utility I made very early on in my operating system. And basically all this does is it gets around the hassle of having to use the a terminal or anything. And while I have written a big terminal program that's it actually functions and gets you, like, it prints out, it handles new lines, it handles tabs and everything, and can push things and actually like push strings to the terminal so they appear on new lines. This one right here is meant to be much more simple and literally just spit out in the first memory location whatever string you push into it. So I have this alert error function and I have this alert warning function. So let's just go over what this is doing, right? So it's not going to return anything, but what it's going to do is it's going to take in a string and it's going to take in a color. And this uint8t color is basically, it's those 8 bits that we're using to store color. Right here. So it's this attribute for color and without the blink. So the first 4 bits are the foreground, the final bits are the background color. Now you're probably wondering what the actual colors are. So let me see if I can get a list of VGA 4-bit colors that we have access to. I just want to know what my color palette options are. I just want the 4-bit ones. Is that too much to ask for? Yeah, so these are the VGA colors that we have access to in hex. So I'm going to take this as a little reference, and I'm just gonna post that in the Discord. So we're gonna be using that to print out our stuff. So we're actually going to treat this function as our kernel main because we are going to directly be writing to it. So what this function is actually doing is, the first thing we're doing, we're casting this memory location to a UN16T pointer, which is basically just a pointer to 16 bits in memory. And essentially, now since we're treating this as a pointer, we can treat the entire frame buffer as an array. And we don't know, here I'm not checking, like I'm not bounds checking. Ideally, I would bounds check for the entire size of the frame buffer. But I don't even care because all I'm doing is printing one line. So I know that the array is much longer than whatever string I'm writing to it, since we're just writing like hello world. And each line is 80 characters and we get like 50 lines or something. So I know I'm not exceeding that frame buffer. So I'm just literally just writing the entire length of the string and not doing a bounds check on the frame buffer, which ideally I would be in a if, but this is just so bare bones that we don't even care about doing that bounds check at all. So you might see that I have string.h. I don't actually have string.h. This is my own custom string.h. So I've written my own string len function. I do get access to stdbool and stddef only because they are called freestanding C libraries, as in they don't have any code associated with them. They are exclusively type defs and defines. So I do not actually, so I am allowed to use these. And these are like the only things I'm allowed to use. Excellent, Braden. I'm glad that you have everything working. So you can copy whatever, you can copy that assembly program that I went over to whatever you're doing. So let's go back and actually create now. We're going to call this kernel.c. And this is actually going to be our kernel. So what do we name our kernel? Well, we name our kernel. We say we're calling kernel main. I don't like that name. I'm going to call it kernel main without the space and with a capital. So kernel main, I'm going to say that this is void kernel main, and we're not going to take any parameters because we're calling this from assembly. And while you can pass parameters in assembly, it's not fun, and we are not. I don't enjoy it, and it's dependent on the compiler and everything. So when in doubt, void everything unless you're calling it from C. So what else are we going to need here? We are going to need our string len utility just to check the length of the string that we're passing in. And let me go grab our string len utility from string.h. I'm not even going to put these in a separate file. I'm just going to put this all in the same file. And I'm also going to be taking our stddef and stdbool with us. And now we're going to be moving back to kernel.c. So now we have our string length function. And we define an int.h here. The int.h header I made was just for basically short versions of the UN18 and everything. So we're returning the size t. So the size t is actually just an unsigned long, which basically means this is the largest possible integer on the system. This is a 64-bit integer. Anyway, so string length, good. And then we're taking in a thing of characters. So now what we're going to be doing is quite literally writing to our thing with the alert. So I'm going to literally just be using this as our main. I never actually finished going over what this does, did I? So yes, we're casting this basically to an array, and we don't even specify the length of it, but we know that we're not going to exceed it, so we don't care. And then we're essentially going up to the length of the string. We're going through character by character and setting the buffer equal to, at the index, to basically the character. And then this right here, this is or, and then color shifted up by 8. So what this is doing, this is taking our color attribute and then moving it up 8 bits into those other bits, and then we're oring it to basically set the bottom bits to the character that we want. And basically all this is doing is taking the color that we've given it and the string that we've given it and arranging it in the format that we want, which is this format right here, where the character is down by the bottom and the attribute is shift. That's why we're doing the shift, right? Because we're starting with the color in bottom 8 bits, and then we're shifting the color up to the top 16 bits, and then we're oring it, which is basically copying down the character into these bottom 8 bits. If that doesn't make sense to you, what's that, Brandon? Are you writing this inside of the WSL Ubuntu files yet? No, I'm actually doing this on Windows right now, but I could be. easily could switch this over. So what I'm actually going to end up doing is clicking on this, and oh no. Can I open this folder in WSL? How do I switch this over to WSL? Because I am going to need to do this in WSL. I might actually just be able to do, for me, I can just type WSL here, and it should just connect me right up. So now I actually have access to this osWorkshop folder right here. But essentially, it doesn't matter where you're putting the source code as long as you have access to WSL to compile. Does that make sense? You can write this anywhere as long as you have access to a command line that has access to that location. Yeah. So, okay. So we have our string length function, and the string length function, pretty straightforward, right? All strings are suffixed with a null terminator, which is 0. So we can just while and then len ++ until we hit that 0, and then return our len. Does everyone understand string len? This is a pretty straightforward function because all strings end with a null terminator. It's just given to it by the C compiler, right? So let's actually finish going over our guy in here. So essentially, yeah, we're setting up our buffer and sending a character to it. So I'm going to take this code right here, and we're actually just going to literally use this for our kmain. Okay, so you know what? No, let's we'll give it its own function. So we'll create our own print function. So this is going to be fun. Void print, and then we're passing a char pointer for our string, and this is our str, and then we're going to pass a uint8t color. And what a uint8t actually is just a char. So this is char color. Char is just a byte. So let's finish this up here. Oh, they actually want us to use okay, because I could type short here, but it's better to use their special named with integers, which are defined to be the right things. So I can include stdint because it is freestanding and is only type defs. As you can see, it defines uint16t to literally be an unsigned short, as in 16 bits, which is why it's uint16. That way we just know the length of it off the top of our head, right? So I'm also going to just use their syntax here for that. So I'm going to do uint8t just to keep things consistent. We're passing an unsigned 8-bit integer. That's why it's uint unsigned 8-bit integer type. Underscore t is type. That's why you also see size type. Anyway, so now that we have this, we should quite literally just be allowed to call print hello. And what colors do we want for our foreground and background? We're going to have to assemble that using this hex character. So that means the first character of our hex is going to be the, let's check it out. Background color comes first, followed by foreground color. And we can use any of the colors that I listed right here in the Discord for those colors. So we have black, blue. Let's say, what do we want for our background? Let's do black as the background. And then for our foreground, let's just do, how about, let's do something fun. What's red? White? White? Okay, that's kind of default. I wanted to show off our bright white. I actually think bright white is not the default. So yeah, let's try it. What's white? It's a F. So we're going to be passing in 0F. And of course, the 0 is the background, and the F is the foreground. So this is bright white. Background is black. Okay, so let's actually, now we actually have to, so our operating system, the logic is done, right? All of that's done. But the fun is only just beginning, because now we actually have the build. And the build process is going to be interesting, to say the least. So the first thing we're going to have to do is pull up our, let's get our linker script. So I'm going to send this to everyone, by the way. I'm going to send the boot. Let's take boot and send it to, can I open the folder? Open, reveal within File Explorer. Yes, yes. Please let me drag this. Of course, they're not going to let me drag that. Let me just send the text then. So I edited this to have kernel main. So if you want to edit this in your copy as well, Braden, since you're probably the only one who's following along right now, there's the current kernel main. And for all those of you who are going to watch this on YouTube and try this yourself later, here is kernel.c as well. C, and we're going to post this in. And now, finally, the last thing that we're going to want to touch is the linker script. So the linker script, oh, did I? Yeah, so I actually, I had slides for these. And then we're actually going to have to go over these building steps. And then that's the entire workshop. So let's go over the building steps next. Because the final thing that we're going to need a few more things. We're not done just yet in the bare bones thing. So yes, we have that done. We could compile these right now to object files. But the first thing we want to do is write this linker script. So this is their special linker script that they've written. And we're basically just going to use the exact same thing that they've written. So let's go take their linker script and put it in. So I'm going to new file, and this is going to be linker.ld. And this is the linker script, which, again, I went over this earlier. This script right here, this file, basically tells it how to set up the boot and the C file once we compile them down to objects, and where to put all of the different sections from the assembly files once we compile them. So let's actually get cracking and moving on compiling. So the first thing that we're going to want to do is compile our assembly. And the way that we're going to be doing that is by using our assembler that we built ourselves from Binutils. This is why we built Binutils, all for the sake of this one step, being able to call the assembler on our assembly file. So I need to actually get to the, I actually need to use the thing. So it's the actual path to the assembler, which I don't believe I have set on this window, but I have set on this window. I believe we did export, so this prefix is the actual location of it. So if I take the location of this and I type, okay, $home, osWorkshop, cross, and then bin, and then i86 elf AS, so -- version, this is our assembler, right? Yes, okay, so this is our assembler. Okay, so that's targeting our operating system architecture. So now what we're going to do is we're going to pass in the parameters to compile our boot.s file. So let's, it's literally just the name of the file, and then our output file is the boot.o, and that's an object file, which is going to have stuff that we are going to then link that to the object generated by our C file. So we're going to output boot.o, and we're going to call it and we're going to call this on boot.s. And now you can see we have boot.o here. And can I make this any bigger? I should have done this earlier for everyone. My apologies. That made the terminal bigger. Oh, that made everything bigger. Okay, good. So next thing that we want to do is actually compile our C program. The C program is a bit more complicated because we have to specify that we're using freestanding libraries and we're using GNU 99 C syntax. We're going to output all errors and warnings and everything. And so let's take this right here, and this is essentially what we're going to be running, except now, instead of running AS, we're running the GCC that we built from source. And now we have our kernel object file. So this contains our source code in binary, but the thing is, now we want to link these together, right? Because boot.s is calling code from this kernel.o file. And now they're both in machine code format, essentially. So now we just have to link it all together into one file where when we call kernel main here, it's calling kernel main in this other file. And I could do an entire workshop on how linking and compiling different programs in C works. And this is a very interesting topic, but I'm not going to go into it because we'd have to get into symbol tables and everything. And that is not the goal of today's workshop. The goal of today's workshop is quite simply just to get the operating system off the ground. So let's actually perform the link right now. So I'm going to take the i638 script here, and let's actually wait. Is this the no? Okay, so here's the link script, right? We're going to take this. This is what's going to actually do the combination of what we have right now. So let's get this down. So it's the same thing as last time, actually, except we're going to be varying the parameters. So let me pull up the parameters right here, T linker LD, and then this, I'll explain all the parameters in a second once we get this up right here. So this T is telling us this is telling it to pass to the linker. So we're passing our linker script to the linker, and that's going to actually follow all of the instructions we're providing right here. We're going to output the file myos.bin. And this is going to actually be our operating system in binary format as an ELF file. You can name this whatever you want. I'm going to call this HelloOs. HelloOs. And then freestanding tells it, oh, we're not using any of the other C libraries. We are only using freestanding libraries. And if you remember freestanding libraries, these guys right here, we are running optimization level 2, which honestly we don't have to do, but we're doing it anyway. No stdlib, again, not using the standard libraries. And then boot.o, we're taking in, this is our inputs right here, boot.o, kernel.o. And then finally, we're doing lgcc to link the GCC standard. What don't they like? Undefined reference to kernel main. Oh, because I presume in here I didn't. Do I make kernel main global? Where are they? Undefined reference to kernel main would mean they think I'm calling, but I don't call it kernel main. Do they? Oh, it's probably. It's not the linker either. Huh. Let's see. What's the issue? In boot.o. Well, did it not? Oh, it's because I didn't save it. That's why. Okay, time to recompile the boot. Nope, that's the version. We are recompiling boot.s into boot.o, and now we are recompiling. Oh boy. Let's see. What do they want? In function start undefined reference to kernel main. But we have kernel main. That's why we're linking them together. Boot.o, kernel.o. What if I put kernel.o first and then put boot.o afterwards? This probably won't fix it, but that is sometimes done the trick. It's probably because I spelled kernel wrong. I'm calling it now. I probably called one kernel and the other one kernel. Let's see. Nope, that looks right. Kernel main, kernel main. Why are we not linking? This is the question on my mind. Let's see. Okay, void kernel main. Let me take a look at the symbol table, because now I'm curious. So do I have the symbol table on here? What is to dump symbol table? So well, dump symbol table. It's nm, not ns. nm boot.o. Okay, so it has all of that, has kernel main, and let's dump out kernel.o. Uh-oh. Kernel.o has no symbols, no public symbols. It's optimization level 2. It's totally optimization level 2. It doesn't realize that we actually need to export these. That's why. Okay, so I'm turning optimization level 2 off because it apparently, since it's set, it doesn't realize that we're actually using all of these. So we are not going to optimize. So I'm going to go O0 so we actually keep these in. And now what are they complaining about? Still undefined reference to kernel main even after. Oh, because that wasn't the right one. I didn't compile the right thing. I want to compile to, where's my kernel O compilation? Here it is. Okay, so instead of O2, we're doing O0 now. And now we are going to try recompiling this, and they still don't like that. Well, let's check kernel.o. Kernel.o still has no objects inside of it. Why is it not outputting the objects that we are defining? I'm literally laying down these objects right here, and it is not compiling. It's not listening to me and actually putting them out. Let's see. How can I get this to keep it is the real question here. Because we are calling it, but we're calling it through here. Kernel.c. What's the C doing? Is that telling it to keep the symbol table? I wonder. We are encountering, as you can see, a few unexpected errors here in the final moments of our operating system. But I will persevere, and we will figure out why the symbol table is completely empty. And I have a sinking feeling that I've probably spelled something wrong, and that is the reason why. Oh, there we go. Now we actually have stuff. That I ran that though. Why didn't that work the first time? Okay, and now it compiles perfectly. Okay, and now we have HelloOs bit, and this is our operating system now as a binary ELF file, and we can actually display this if we want in a hex editor and check out the fact that it's an ELF thing. And we can actually probably find the symbol table down in here somewhere. We can find all of our machine code. As you can see, we have a big empty space because we've skipped over 1 megabyte at first. Let me actually make this smaller. You know what? No, I'm not making this smaller. We are literally just going to compile this to an ISO, and then we are going to be done. So let's actually get the ISO set up. So there's 2 more things that you have to download if you haven't downloaded them already. And that is, if I go over to General where I have them, it is grub PC bin. Actually, it's 3 things. My bad. So yes, this is a very Pog Pepe moment, Matt. I agree. So these 3 things right here, these 3 utilities. So the first thing that we have is grub common, and grub common is basically what we're going to be using to make the ISO. Grub PC bin is, I actually have no idea why we need that, but it's a requirement for grub common to output things in the right format. And then XOR.iso is actually the program that basically creates the ISO behind the scenes for grub common. So you're going to have to sudo apt install all of those. Thankfully, I've done that already, so we don't have to sit here and wait for those to install. For those of you who are following along, install these 3 things right here. Sudo apt get on all of those. Sudo apt get install all of those. Now, we can actually run, finally, at long last, if we go back to our suffering, we can, where is it? Oh, they're not actually going to give us the they're not actually going to give us the instructions, are they? Is this? No, that's the cross compiler. Why am I sending the cross compiler? Okay, this is where things get fun. Okay, so now what we have to do is we have to create a CD-ROM image essentially, and the first thing that we're going to do for that is we're going to basically specify a special grub config file, and I am literally going to, oh boy, we got warning, end of file not found at the end of line, no new line insert. That is because in your boot.s, you do not have a new line at the end, because when I post on Discord, you probably have this, it has to be bad. It needs to end with a new line, or it's going to throw out that warning. But that's just a warning, it doesn't actually matter in the long run. Yeah, don't ask me why they do that. It's an interesting quirk, and I get that error a lot. It's because I always forget. I'm like, why do I need an empty line at the end of my file? It's like you need like a double new line to end the file or something. Anyway, let's actually create our grub config now, and this is going to be a pain. But essentially, what we're doing now is we're just setting up what we need for the ISO to be generated. So let's go over to the operating system I have and take a look at what they have. So they have this grubs.cfg file. And essentially, we're telling it that it's multi-boot, and this is the location. We're writing to the boot partition with our binary, right? I think that's what that's doing. No, that's in the boot folder, question mark? Build folder? Build boot? I'm actually not entirely sure what they think they're doing there. But I'm just going to basically copy our grub.cfg file over. And we're going to make a new file. This is grub.cfg, right? And let's paste this in here. So our menu entry, we're going to call this, what do we name the operating system? HelloOs.bin. Okay, HelloOs. So we're naming our operating system HelloOS just because we can, right? So I'm going to call this, so of course we have to actually specify. So this is our grub.cfg. I'm going to write this into the Discord as well, right here, as you can see. So from here, what we actually need to do is use this to generate our thing. So the first thing we have to do, we have to set up this really convoluted and stupid OS directory structure that they're going to want. So I'm going to run make dir in here, and we're going to create these 2 directories in here. And this is going to be our ISO dir. And basically, we're setting this up to be put onto the disk. So the first thing we have to do is then we have to copy our binary, and then we have to copy our config into this structure. And then once we copy those into this file structure, we can run the command to make the ISO. And once we have the ISO, that's what we can run on a virtual machine. And that's going to be beautiful once that happens, because this workshop has gone on for about 2.5 hours now. Thank you for the few dedicated people who have stayed and waited it out, all for one line to appear on the screen. But you've gained invaluable knowledge about how to develop your own operating system. So let's go back and finish this up. Essentially, we made our thing. Now we are going to copy our operating system binary that we've compiled. And of course, we're calling this HelloOS, HelloOs.bin. And we are copying that into our new structure. And the reason we're making this file structure is, again, just because the ISO expects this file structure in this order being input so it can create the ISO. So we're copying this in. So now you see that the ISO.dir actually has our bin in its root, and it has this grub folder in here. And now in the grub folder, all we have to do is put our config folder file that we just wrote. So we're going to copy this in to home boot grub. Yes, so, and now you can see in our grub folder, we have our grub config. And now at long last, and remember, this is only going to work if you've installed these 3 packages first, we're able to run our grub make rescue. And the real reason you're supposed to do this is to make a rescue disk, but you can use this essentially to create an ISO disk. And this may or may not work on the first try. I might have to run some black magic command as well if this does not work. But let's make an attempt. So this is going to be HelloOs.iso and ISO.dir. And ISO.dir is, of course, the name of this file structure that we've just created with boot and everything. And let's try executing the command, and let's see what we get. And we have successfully created HelloOs.iso. And now, if we want to pull up VirtualBox, and if we want to create a new virtual machine, and I don't really care where it's stored because this is so small. Actually, I do care where it's stored because they're going to think this is a real operating system. So I'm going to put this in my D drive, in my VMs folder. I believe it's in software, VMs. I'm going to call this new folder. Oh, God, it closed. Why did it close on me? Stop. New folder. No. Folder. HelloOs. Yes, select folder. Okay. HelloOs. It is not Microsoft Windows. It is other. The version is unknown 32-bit, not 64-bit, important. And now we're going to name it HelloOs. HelloOs. And then next, the memory size, we're going to give it about 512 megabytes. Next, the hard drive, we are going to not add a virtual hard disk because this operating system, at no point does this operating system ever use the hard drive. There is never a hard drive involved in any of this. We are loading it off of the ISO. A normal operating system, you load the ISO and then it installs itself to the hard drive to boot off of the hard drive. We are always booting off of the ISO. We have not written in the functionality to do the install to hard drive where we copy ourselves and the bootloader over to the hard drive. We do not do that, so we do not need a hard disk. We're going to create it. You are about to create a disk without a hard disk. Yes, I don't care. And then we are going to go to our settings. And now this is where we have to mount our ISO. So if we go to our storage, and let's see if I can actually add a thing into our disk controller. So I would like to add a new disk. Choose disk. And now I can actually get the disk that we have just generated. So if I open this in a new file explorer, not boot, I'm going to take this. We're going to go back to our other thing in VirtualBox. I'm going to put this address in. And here is HelloOs. We're going to load that in hello.iso. I'm going to choose that. Choose. And now we've mounted this. And I'm going to say, OK. And let's try running our operating system. I'm terrified. Oh, here we go. So this is grub. Grub is the multi-boot. So it's detected it. Grub has detected our operating system and is now saying, is this the operating system you want to use? So I hit enter, and now it's going to boot. A critical error has occurred while running the virtual machine, and the virtual machine has been stopped. Well. Okay, so we have failed. Unfortunately, the first attempt has indeed failed. I'm very interested in what has failed. Let's take a look. So that was a good attempt, good first attempt there. But clearly, this has not gone as planned. So let me go take a look at my black magic command to see if I can fix the rescue command. And from now on, I'm actually going to be executing this using QEMU because it's way faster for me to develop with QEMU than it is to develop without QEMU. So let me go take a look at over here. What am I doing different here? Let me take a look at my build script. Okay. Quiet build, yes. Build ISO source gets put to dev null or echo build failed. What am I doing wrong here is the question, because it all feels like it's right. But obviously, something wrong is going on. And we want to figure out what exactly that is. So I'm going to take grub make rescue quiet build ISO name, and I don't know why I'm funneling build ISO source to dev null. Is that because build ISO source? Oh, I think I'm deleting that afterwards. No, I'm curious. Let's take a look at what could possibly be going wrong here. Do I have QEMU system just available? Is this a thing I can run? I know I have it. I've just been avoiding running the QEMU instead of VirtualBox because it's a lot slower to get this found out. If I go here, if I go to software, QEMU, where are you? Programming, QEMU. Here we go. Okay, so I want QEMU for, where is he? This guy. Okay, so using this, I didn't want to have to do this, but I'm going to do deprogramming QEMU I6 8. Is it 8? It's probably not the actual. That probably ends with it. QEMU system. Okay. System i36.exe, and then we're going to pass in our ISO, and this is actually the wrong terminal. Great. Let's go back over. We're going to exit WSL. No, where is the right one? Here we go. Exit. And what is the name of our operating system? HelloOs.iso. Now let's wait for it to boot up. Image format was not specified for and probing guessed raw. Automatically detecting the format is dangerous. Okay, so maybe the issue is that we've written it wrong. And as you can see, we're not printing. And it looks like the issue is with the image format. So that makes me very suspicious. Let's not screen grab. Control-Alt-G to undo QEMU. Image format was not specified. Despite the fact that I have grub.cfg. Do I have grub.cfg in the right place is the new question. Is this the right location for everything? I just want to make sure everything is perfectly set up. QEMU system. I forgot CD-ROM option. Let's try that. -CD ROM. Hello ISO. And now it doesn't give me the error, but we're still not running. So let's figure out why exactly we're not running. Let's go to boot.iso or boot.s. Take a look at what's going on. First, stack top ESP. We're calling kernel main. Good. Section BSS. Good. Okay. Let's take a look in kernel.c. I imagine whatever error is happening, it's probably going down in here. Passing in the string, hello, good. Character, the color is fine. I don't think that's the issue. We don't have to return. Good. Right. String len should be working fine. Well, this is rather confounding because it looks as if everything is properly set up, but unfortunately, it does not seem to want to cooperate, and I will be very sad if I just spent the entire day setting this up, only for it to fail at the last moment. However, we are bordering on almost 3 hours, so I would feel bad holding everyone here for me to finish testing this, but I would very much like to figure out what in the world is going wrong here. All right, what if I go back to WSL? We do some debugging. Let's take a look at the grub build. We have now grub make rescue license blah 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 installed. Where is the? I feel as if something is off about this. The boot my os.bin. Have I incorrectly made one of these letters capital or lowercase when it shouldn't be capital or lowercase? Boot hello no, because that's in the right directory still. ISO dir grub.cfg, and the grub.cfg got copied over perfectly fine. It's probably because I'm not in LF format, isn't it? They're gonna yell at me for that. Let's see. It's entirely possible that the issue here is my indentation, and that's just screwed everything over. I genuinely would not be surprised. Let's check if this threw any errors. No. Okay, good. Grub make rescue. We're going to try running QEMU again on this. Of course, we have to exit to run QEMU. Exit. Oh no, they are not seriously about to make me copy QEMU over again. Well, I'm not doing that. I'm just going to go grab my build script from the other program that I have. Build.sh. And then I run, to finish this off, I run QEMU path. I'm taking this. I'm stealing this. What's my QEMU path? Literally just going to set it. Oh, wait, that was it. Oh, that's the wrong thing. Okay. Back to the other one. QEMU path system i386.s crom build os name. Wait, what are these? QEMU path. So the QEMU path is quite literally just D. I have to grab the path. Hang on. It's programming QEMU. There we go. At least for me. And then you gotta fix the backslashes. Cannot open build.iso. The system cannot find the path specified. Oh, because I left it like this. Brayden, how's things going on your end? Does anything, are you getting the same error? I'm curious. I completely agree. This is by far not open build. Oh, because it's not called build. It's literally just in the root directory. Guest has not initialized the display. Oh, because this is debugging mode. I don't want debugging mode. That's what the S is a. It's not what I wanted. Not what I bargained for. So I like how it detects it, but it just doesn't actually see it. Control-Alt-G. Is it the linker? Am I doing something wrong in the linker? I feel like there's got to be there's something I'm not seeing somewhere. Start is correct. Global start. Yeah, good. T linker OST before things stop working. Okay. Did you what exactly hasn't started working? Because I'm curious about what actually is going down right now. I'm very curious about what is and what isn't working. Actually, one thing I can do is I can check the symbol table of the binary. nm HelloOs.bin. Well, it looks like we have everything. Start, good. Kernel main, good. Print, stack bottom, stack top, string length, def loop, good. All of the flags exist. which confuses me because this looks everything looks to be in working order, unless, of course, we are incorrectly writing something. Fix the bug. It is spitting out loader syntax error. Looks like there's an error in the loaders, the linker scripts. Huh. On line 2 of the thing. Maybe Discord changed the underscore? Did I send the linker script? I think I did. Did I? No, I didn't. Oh, I guess I didn't send the linker script. Well, that would explain everything. Okay, let me send the linker script over. Hang on. My bad. I'm pretty sure I'm using the exact same thing they gave, because we are quite literally just using the same sections and everything. It's all the same, unless what's going on here is the fact that they throw in a RO data section, and I'm completely ignoring the RO data section. But I don't think I deleted an RO data section. I think this should be saved. Move stack top. Yeah, okay. So that's normal. BSS section is still here. The multi-boot section is here. So obviously, since we're able to detect the operating system, something's going right, but also something is going wrong. And the bigger question is what's going wrong. All of our symbols are in check. The question just becomes, what is the one piece that's not falling into place? What if we try writing with a default color instead of, I'm suspicious that it would be the color, but you really never know. Let's try writing with red on red. Sure. Kernel.c. And honestly, at this point, it would probably be best for us to make a special script for this. Okay, passing the color. Color is good. I know that this function has worked in the past. As for whether it works now, is a separate question entirely. And this is the right address. We're casting to N16 pointer. String length should be good. String length, yeah. Char, hello, yes, that's fine. 6, good, okay. Let's try some recompilation. WSL. Grub, make rescue. No, we want to go all the way back up to where we're actually compiling stuff. Okay, so the first thing we want to compile is, all we have to want to compile right now is the kernel. And actually, I am going to compile with O2 now. Let's check if that deleted the symbol table. nm kernel.o. No, that didn't delete the symbol table. We're clean. Okay, so I don't know what I changed in here, but I should probably save everything before I do anything. Did I not save grub.cfg? Wait, if I didn't save that, that would be the region that didn't work. I save both of these and the linker. We'll make one more attempt, one more solid attempt, and then we will give up because it is almost been 3 hours and I do not want people in the club to suffer. Okay. Good. Let's take a look at our symbol table for the final output. Hello. I swear to God, if the reason that this didn't work was because I didn't save it, I'm going to be livid. I feel as if that would probably be one of the reasons, though. I have no faith. Okay, so now, unfortunately, I have to redo the copy and everything. Okay, so copy the binary to there, and then copy the grub config, and finish it off by doing grub make rescue on the ISO dir. Rota hello dir ISO, and now I'm literally just going to copy the script because this is going to take too long otherwise. I'm going to just take QEMU path. I'm going to take this directly out of the build config for the QEMU path. And I'm going to declare that, and then I'm going to run the script that I put in my original build script. It's unfortunate that I didn't have enough time to write a real nice build script for this one, and I didn't have time to get debugging up, because on mine I'm actually able to just put a breakpoint here and then just run F5, and I can immediately have access to all of my functions, and I can actually do a step through it. So as you can see, we've oh, it's broken because I actually just made an edit to this. We're not going to look at that. We're going to go over here and just finish what we were doing. QEMU path system.is. Yeah. CD-ROM ISO build name. Do it. What don't they want? Build.iso. The system cannot. Oh, that's right, because we're on a different thing. It's not build ISO name. It is literally just the ISO name. HelloOs.iso. Guess it's not initialized display yet. Of course, I still left in the debug flags, which we're not using because we never set those up. OS. Oh my God, it worked. Oh my God, it worked. I don't even know what went wrong. We did it. It was probably because I forgot to save. Well, everyone, thank you for coming to my workshop. We have successfully developed an operating system. We have red hello on blue background. Thank you for sitting here for 3 hours. I know it was painful at times. Things didn't always go the way that we wanted them to. But now we have successfully finished a very basic operating system. I will push this to the GitHub for anyone who wants to play around with these files and everything. And hopefully you can use this, the 3-hour talk that I think June's going to be uploading to YouTube at some time tomorrow as a reference to hopefully develop your own little operating system. So before I end the workshop, should I even say that? I should just end the workshop right now. But before I end the workshop, I just wanted to talk briefly about the next steps, right? Because we have this nice console. We don't actually have the ability to do anything with this. The next step is to get keyboard input. But to get keyboard input, you need to have interrupts enabled, because when you press a keyboard key, it calls a hardware interrupt, and you have to write interrupt handlers. And the way to do that is to set up a global descriptor table, or not a global descriptor table, an interrupt descriptor table. But before you set up the interrupt descriptor table, you have to set up the global descriptor table. So you can see in my little attempt at building on this operating system, the first thing that I do in my kernel init is actually called GDT init, and I haven't even gone to the point of writing the interrupt descriptor table yet, but I have successfully created a global descriptor table. And if we actually take a look at my core lib, I have gdt.h here, which basically sets up a global descriptor table entry. So I'm on my way to getting keyboard input, but I hope you understand just how painful this can be. If you're interested in helping me out on developing an operating system over the coming weeks and building on this, we need people to help write C libraries, because as you previously saw, I have like 5 string functions. It would be very nice if we actually wrote our string.h library to comply with the C standard and have all of the string functions. And same with math and everything. So, and also we can write our own special libraries with our own data structures. And, because normally by default, the C language doesn't come with a binary tree. It doesn't come with any like fast search methods. It actually does. It comes with binary sort and binary search. Binary sort. It comes with binary search, and I believe it also comes with quick sort. But we can implement all of that ourselves as well, which is very fun to do for those of you, especially in intro level classes, if you haven't done that yet. But yes, if you want to work on the Winterside Project Initiative and have operating systems be your thing, this has been my this week has been my big advertisement to work on the project with me. So if you want to help out, feel free to reach out. Emily already reached out, so we're probably going to be working on this in the future at some point. If anyone else wants to hop on, just feel free to let me know privately after the workshop, or just at any time. over winter break. And we're always taking new libraries if you want to write a little standalone library. Keep in mind, you're not allowed to rely on any of their libraries. You have to write it fully from scratch. Anyway, with that, how's Brayden? How are you doing? I want to just make sure that you're you got everything good to go before I end the workshop. See if we get some results. If at least one person here got the results that we wanted, it's good enough. The fact that even I was able to reproduce it makes me think that this was good enough. But we will see. Did I send? I probably didn't send the thing either. I should have sent the grub config and everything as well. We send over the grub.cfg file. This is grub.cfg in Discord right here. The copy grub config. Not sure what I do after the next command. The next command's the thing that's actually supposed to create it. So you're going to. I don't want this. It's because we're in QEMU right now. Control-Shift-G. Okay. So after that, what you're going to want to do is grub mkrescue o, and then the name of your ISO, and then the directory. Your do -o ISO HelloOs.iso or whatever your name is, and then ISO dir, which is basically this structure that we're turning. This file structure is what we're turning into our disk, right? Our rescue disk, our ISO, and then once we have that ISO, we can either insert it into QEMU or we can insert it into VirtualBox. And now that VirtualBox is working, actually, let's see if we can. Let's actually try seeing if we can get this working with VirtualBox. Let's go to our storage, and we're going to remove that. And now we're going to insert a new one, new disk. Choose disk. That's the wrong hello.iso. We're taking that out. I'm gonna search a new one. This is our new HelloOS. Choose. Okay. Let's see if it works on VirtualBox now. VirtualBox. HelloOS detected. And oh, look at that. Works on VirtualBox as well. All right. So if you got it built successfully, the only thing you have left to do is to run it on VirtualBox. And it has now officially been a 3-hour-long workshop. This is the longest workshop we've ever hosted at the IEEE. The fact that there's even still people in this call is absolutely insane. I kind of expected everyone to leave. But good work. Thank you for staying. Where is the... Yeah, don't forget to save. Don't be like me. Don't forget to save your grub config and then have it instantly announced that you have a crippling error.